Sí. Claro. Muy bien. Ahora. Ahora.
¿Qué pasa? A ver, la identificación, ¿qué vais ahí? ¿Qué vals?
Esto se llama vals. Es que te falta de empresa, tío.
¿Cómo se llama
vals? ¿Cómo se llama vals?
Sí. Estaban vendiendo batch en plan de bachiller, ¿sabes?
No.
El badge, sí, el badge. Sí, tenemos ¿qué era badge? Badge, ¿no? Échate una foto, pero desde la lejanía, ¿sabes? Te la saca entonces, te la saca una foto. Esto sí debe tener así como que ahora, por ejemplo, cuando la gente que de la casa
Yeah, I had to run away to basically did all the nice stuff. It's just amazing how it works. Particularly work that one would not like to do. Creo que dilucio, mañana la necesitamos. Bueno, sí, sí puede hablar. Sí, ¿Tú estás en contacto con Alicia, Manu?
Sí. Si quieres, podemos
Alicia ha dicho que hablen con
cosas que he hecho con la
¿Qué cosa? Se paga de parte con los 5 minutos. Los viajes más fáciles, si tú luego pasar con los coffee breaks, con el servicio técnico, esto como factura, pero eso lo tienes que hablar.
Normalmente lo que hacemos es que se ha preguntado por tu precio final, porque eso ya no tiene las tickets.
Sí, pero bueno, aproximadamente es que necesito saber si lo que falta de contribuciones, pero eso está bien, es que mientras está por debajo de 10.000.
Sí.
Y incluso un poco menos, porque con el otro me... Vale, perfecto. Si vamos por debajo, sí, perfecto. Porque esto hasta 8, no hay problema. Tienes que hablar con ellos. Lo que menos trabajo es, para ellos les encanta si les das una factura, el concepto de...
Sí, de cada uno. Fue un follón en
cualquier habla con ellos también. Un follón que
y aquí está la persona. Aquí las mapas de la dirección, llevar el patrón. Lo que está aquí en verde es el continuo en todas las verificaciones. Anatomía, misión, estructura, la línea de misión como más real.
Sí.
Todo el agua central.
Solo una
y con un poco de estructura de huevo frito. Y esta es la que más estructura tiene. Toda más o menos.
Pero la estructura es bastante básica, ¿no?
Tú trabajas todo.
Es que no se resuelve en realidad. Tiene aquí este círculo de aquí. Cosas que estén dentro de este círculo.
Y también el primero este STARFORM.
Exacto, ¿verdad?
Con esta línea, pues he hecho los ratios, H alfa, H beta, la extensión. Aquí está de excitación.
Entonces las 8 de platitas o de...
El diagrama BPT. Una persona lastra el diagrama BPT.
Se quita una grabación.
Yo voy a la cena, aunque no he pagado, eso es
Inversión de la temperatura.
Sí, perfecto, sí.
Claro, sí, pero lo haces en los inversores, ¿no? Sobre todo el mapa.
Perfecto, esto es que cuando tienes los dos, ¿cuántos
Y este el estudio como varía todo esto con el radio, ¿no? Aquí está H sobre H beta, de 0 a y lo cual se
tranquila la sesión.
perfil promedio, como que da una estimación de
Sí, especialmente tengo variables de
sí, con el radio, de parte del centro de estado.
Sí, esto lo hacemos ahora ya. Esto ya algo nos pasó y
Es complicado, ya te digo, interpretación más solo diagrama de PT. Integrados. Pues aquí la longitud de la metalicidad. Tenía la más estelar, están aquí. O sea, tenemos la galaxia normal, pues tiene como una conversión rey como toda
Hicimos las encarnaciones de perspectiva ya, es el plan. Ya,
Yo entonces no cinemática y tal, de texto un poco más creído, no trabajo o sea, nunca trabajo con
justo el efecto ahí está.
no contestaron.
Que tengo menos intuición con los números en cuanto a velocidades.
Es un poco a poco. Pero bueno, eso es el efecto Doppler.
No sé.
Estas son las mismas, los mapas de velocidad, estudiando líneas de velocidad.
no, nada. Es que yo me pongo nervioso con todas estas cosas. Y entonces al final he mirado un poco y pensaba todo bien y al final es que la artística he dicho, mira, esto y ha dicho, no, pasa nada, está todo hecho. Ya, puedes olvidarlo todo, está todo hecho, me ha dicho.
Pero aquí no, ¿sabes?
Yo estoy paranoico ya.
Recuerda que aquí dos cosas, lo que pasa es que están en el mismo sitio, uno está delante tuyo y otro detrás. Y hay un criterio que te dice un número de o sea, aquí puede haber también un gran tranquilo, una velocidad muy intensa, y también puede haber gas con mucha velocidad, sería una de las cosas más me encanta aplicar, pero todavía la parte ancha de los perfiles, aquí se ve alguno, ves que está hiperancho, una estrechita, también hay criterios para decir que no, dos, tres, este de aquí sería como el efecto integral. Lo sumas todos los efectos de aquí y lo pones. Pero en cada fase le has ajustado solamente una única opción. Si va a la derecha o a la izquierda, si es más ancha, más pequeña, le cambia el mapa de todo ahí. Luego aparte pues, hay imágenes del Hubble, de mucha
Savannah, yes, I remember your name. You're lucky to do that. Smart, friendly, hardworking. It's also good. Very hard. We wrote this proposal to weapons.
Creo que
Okay, so we have had the usual stress of the bill not coming on time, I guess. Yes, right? That happens always.
Don't touch.
If I dislike something during a lecture, are we? I think we're still missing a bunch of people here. Or they were scared off in the morning.
I am well known. I am well known, intimidating, and
Throwing chocolates at people.
yeah, like I will swear at you while throwing chocolates. Just for extra to rope it out.
I noticed it because students of mine are not here, so I may throw these at them. So we have also, just in case, so we will have tomorrow, we will have whiteboards that Fernando will put up. So for those of you who do not want to post on Slack or on the pad that we have here is also very classical post-it notes. Any doubts or anything that you never dare to ask, also if it's not treated here, as long as it's related to star formation, post here. And you can then take one of these, write on there, stick it on the whiteboard. So I think now almost everyone is back. Amy is coming. I'm still missing a student of mine. Bad for you. Let's wait 2 more minutes. Let's wait 2 more minutes. Need an M&M's pumpkin. Didn't work too much with the sizes like okay. I think we're 95% complete now, so let's start. Oh, yeah. So now our speaker now is, actually I'm not the chair anymore. So.
Yes, I'm the chair. I have to take over.
You're the chair?
At least according to the schedule, I'm the chair.
Oh, cool, yeah. Great. You can introduce this.
This is Johnny. Everyone's saying hi, Johnny.
Well, thank you, Mark.
There you go. This is Johnny. He's going to talk about molecular quantum.
And he has also been very instrumental in setting up the first and also second of these star formation schools, I have to say. So John is from both Heidelberg and Liverpool.
I did a poor job.
It's fine. Hello everyone, I'm Johnny. Welcome back after lunch. Hopefully you're not feeling all too sleepy after the lunch break. So following on from the lectures this morning, I've been tasked today with the internal structure of molecular clouds. And more specifically, I'm going to focus on the morphological structure of molecular clouds. So just to kind of reiterate, I think what Amy said, this is supposed to be informal, right? So do feel free just to kind of shout out, ask questions. If I don't see your hand raised immediately, hopefully someone else with the mic will. Let's keep it interactive. So in keeping with that, I thought we would start with a quiz question. Okay, so I've taken a quote from a paper, and I'd like you to guess the year you think this paper was published. All right, so the quote is, among the most surprising things in connection with these nebula-filled cores are the filaments that so frequently run from them for great distances. These filaments undoubtedly have something to do with the formation of the cores and the nebula within them. So I've modified the words very slightly, the ones in italics, just to bring them kind of into the modern day. But I'd like you to have a guess. When do you think this paper might have been published? I'm going to offer no facial expressions. We'll move around the room, but people do get chucked in fact. Yes, Mark.
No, this is like, it's got to be E.
So this is pre-Herschel. Long time pre-Herschel.
Pre-Herschel is a good start. Yeah, exactly.
Ancient Great.
Wait, pre-Herschel, like
Pre-Herschel
1700s?
Yes.
Telescope.
Not that far. Not that far. Okay.
11 years ago. I went to a conference, we were talking filaments. I suppose, I don't know.
Earlier than that. So,
I was going to guess it's from Barnard.
Barnard is the correct answer, right? So
I get to give myself a
you
chocolate.
get to give yourself a chocolate. I think Amy deserves a chocolate as well. This was actually a lesson in how well you were listening to Amy's lecture, because she also had a Barnard paper on there as well. 1907.
Wow.
Right? So this is actually a photographic plate. You're looking at the Taurus molecular cloud. It's actually, incidentally, it's the same filament that you can see up here in the background image as well, right?
And what is that? Is Herschel now colorful?
It's a combination of different observations. I think Herschel is definitely involved in this one. The point of this is to say that we've been studying the morphology of molecular clouds for over a century. What's actually really funny about this is that what happened between 1907 and the present day is radio astronomy, right? So fairly poor resolution initially. Everything looked incredibly blobby when we first detected CO, and then we went and spent 40 years describing everything as spheres. When we've known since 1907 that everything is actually not spherical, and it's actually more complicated than that. We have these nice filamentary structures. So what I'm really going to be talking about today is the internal filamentary structure of molecular clouds. And so this is by no means a complete overview, of course, and what I'll try to do is point out where and what to read, and of course I will make all my slides available to you at the end of this as well. So some of the slides are going to be quite information dense, but that hopefully will be important going forward. So fast forwarding over a century from Barnard, this is the kind of picture we have now. So now we know that the internal structure of molecular clouds is incredibly complicated, right? In terms of physically, dynamically, chemically, morphologically. Of course, we know that stars are born in molecular clouds. So up here, we're looking at the Taurus molecular cloud again. So just to kind of give you some insight, this is looking at an integrated intensity map. I think this is the 1 to 0 transition of carbon monoxide, but it's definitely some transition of CO. Taurus itself has a mass of about 10,000 solar masses, so compared to what Amy was talking about with Orion, it's about an order of magnitude below the mass of Orion, so it's kind of fairly wimpy compared to Orion. And the scale here for reference is about 20 parsecs, which, is kind of typical for molecular clouds in the galaxy. Within those clouds, though, what we find are these complex networks of filaments, okay? And this is where we're going to talk about today, and within the filaments, what we find are kind of quasi-spherical cores. So here we get down to, sub-parsec scales. This is the kind of thing that Amy was telling us about today, and below those scales, right? So getting out to disk scales and things as well. So my lecture is going to focus on this intermediate scale, right? The internal filamentary structure. So when I was writing the lecture, I tried to think about what might be useful to me if I was a starting master's student or PhD student, and given my first data set and how would I actually go and analyze that, and looking at this structure. So this is the outline. Roughly, I'm going to talk about, first of all, what tools are available to you as new researchers in order to analyze the data. We then want to talk a little bit about how do we actually go and extract information from our data sets, and what are kind of the key metrics that we want to use to describe this internal structure. And then finally, I want to get on to talk about how these measurements have actually shaped our interpretation of how this internal structure actually contributes to the formation of stars. So you can think about this a bit like a recipe book, right? So these are the raw ingredients. We then got the kind of how you're actually going to cook your meal, and then here I'm going to show you lots of photographs of food made by other people. That's kind of the general idea. All right, so what tools do you have at your disposal as new researchers? And I think Mark said this really well, there's no need to reinvent the wheel here. Right? There is a wealth of publicly available open source astronomy software available to you. This is supposed to be overwhelming by design, right? There is lots of things that are available to you. So just as a quick show of hands, who may recognize some of the pieces of software here and who has used some of this in their own research to date? Okay, so a decent chunk of you, so I hope this is going to be useful. Obviously, I'm not going to go through all of these. I've sort of divvied these up into different sections, and what I want to do is just talk about some of the pieces of software that I use all the time, day to day, in my own research, and how I actually go on to use them. And of course, we can talk about this more at the end or throughout the week or whatever you want to do. So first up in this segment is kind of the software that you may use to get a first look at your data. So for example, something that I've been using really recently is Carter. I think this is fantastic. It's offering a really quick way of opening large data sets, and that might be two-dimensional data sets, it could be 3D data cubes, and providing a first visualization of that data. But if you're wanting something that is perhaps a bit more in-depth, perhaps a bit more versatile, so being able to actually apply some methods to that data in addition, something that I can highly recommend is a piece of software called Glue. So this is just a rubbish screen grab of a Glue session, right, that I was working on. So there's different data sets here. The basic idea behind Glue is it offers a really quick and intuitive way of getting to know your data. And that's why I really like it. The other thing, the reason it's called Glue, is because it allows you to link different data sets, right? So I'm showing multiple data sets here, and I'll illustrate kind of what you can do with that in just a second. So what you're looking at here, this is actually the molecular cloud that I studied for my PhD. So this is an infrared dark cloud within the galaxy. It's about 3 kiloparsecs away. We're looking at interferometric observations of that cloud. On the left-hand side here, we're looking at dust emission, right? So this is dust continuum map at around 3 millimeters, so looking at the real cold and dense dust within the cloud. Up here are complementary observations that we got for free at the same time. These are actually now looking at spectral line observations. This happens to be the N2H+ molecule, so this is very good at tracing very dense, very cold regions within the cloud. But now, because we're looking at a 3-dimensional data structure, so we're looking at a data cube where we have access to both spatial and spectral information, the vertical axis here is now velocity. So this is just a volume rendering of all of the emission in the data cube. Right? Here, I'm going to talk a bit more about this in just a second of what I've actually done here. But essentially, I've taken this data, I've taken all of my spectra, and I've identified all of the emission features within that data, and I've modeled them as Gaussian features in my map, right? So a parametric description of all of the emission features that I can see in my data, such that I can describe those emission features, their brightness, what velocity they're at, and the width in velocity as well. And then, because you're moving from something here, which is a kind of a 3D array, a regular gridded 3D array, to something which is now working with discrete data points, this is now a 3D scatter plot, right? So I'm actually just showing the velocities of each of those modeled emission features. And then we've got a simple histogram, and this is a scatter plot of the brightness of the line versus the velocity dispersion, so the width of the line. The neat thing about Glue is you can say, okay, I'm really interested in this stuff here, right? So I'm interested in this stuff which is pretty bright, right, on the y-axis, which is the amplitude. It's fairly narrow. The reason for that might be that you're looking at N2H+, so it's bright, that's a good proxy for how dense the gas is. And then the dispersion gives you an indication of the internal kinetic energy, which you can compare to gravity, and you can say, okay, which regions are likely to collapse and actually form stars in my data set. What that immediately does then is Glue then propagates where that data lies in these other images as well, because you've linked them all. So I can say, okay, where spatially does that information lie in my data set? All right, so it just provides an intuitive way of actually getting to know your data in a very quick way. In terms of statistics, I want to highlight this code TurbiStat. So it's basically kind of a war chest of various statistics that you might want to compute on your data. So it has a whole range of different statistics that you can actually compute here. I'm just showing 2 examples. This is a probability density function here, and then a power spectrum. It also offers not just the ability to compute the statistics itself, but you can actually do parametric modeling of the distributions. So for example here, you might be fitting this PDF with the log normal profile and then some kind of power law. And then here in the power spectrum, fitting this with the broken power law, so that you can have a parametric description that you can then go on to use to compare with other data sets or perhaps other regions within the data set that you're looking at. What's really great about Glue is the documentation, right? So it offers full Python notebooks to actually compute these statistics, how you would actually model that data. It has functionality for creating synthetic data sets for comparison with your actual observations, and all this is documented really nicely with links to all of the relevant papers that actually point out, where you can learn more about these statistics. Something else that we do is morphological classification, right? So segmentation into physical structures in the cloud, and this will be a big thing throughout this lecture. So if filaments are your thing, and we're going to talk about filaments today, then there are algorithms to find filaments, right? So here I'm showing two different filament finding algorithms applied to the same data set. And the first thing that you might notice is there are differences, right? And this is going to be really important throughout this lecture. Not all algorithms give the same result, right? And a related kind of caveat with this type of analysis is that parameters matter. Garbage in, garbage out. So it's up to you as researchers to actually determine what are the best parameters to use and apply in your data set. Something else to highlight here is that these are fairly adaptable, typically. So here I've just applied an astronomical filament finding algorithm to a satellite image of a river in northern Italy, and it's found all the tributaries associated with that river, if that's kind of your thing. And then there's usually sort of sister algorithms that can define or identify properties of those filaments, so widths, lengths, etc. In terms of kinematics, I touched on this earlier, there's a number of tools dedicated to providing an in-depth look at the velocity structure, so the kinematics of the data that you're interested in. So specifically by modeling the spectral line profile, so here is an individual spectrum. Here we're just showing how you might actually fit that data, so you can see as this decreases, we're going to see, so it's a single component, and then we're going to switch to fit multiple components in the data as well, here. What this produces is a parametric description of every single spectrum located within your data cube. And that allows you to go from something like a 3D data structure into something like this, where I have a model for every single emission feature in my data set. All right, so that gives you some insight as to the things that are actually available to you. And so you've got your data set and you've got all these tools, so now what? How do we actually go about extracting useful information from this data, and how do you pick the right tool for the job, essentially? Well, to some extent, that's going to depend on the data set that you're actually working with, right? So you're interested in star formation, I'm going to assume that you're probably working with dust continuums, or either emission or extinction maps. That's going to give you access, as Mark said in his talk today, to column densities, masses, dust temperatures, the physical structure, the morphology as well, and if you have the sensitivity, potentially polarization and magnetic field orientation. Or you can be working with molecular lines, where you have access to many of these things as well, but the key difference being the kinematics. Something that I wanted to highlight here as a slight aside is what to do if you don't have every single data set to answer your science question immediately. So on the single dish side, we basically mapped the entire of the galaxy in CO, right? This is a compilation of various different isotopologues. It might be sort of slightly different transitions, but the principle is the same. So we've mapped virtually the entire galaxy. Each of these galactic plane surveys, or at least many of these galactic plane surveys, will have websites where you can go and freely download processed data, so actually science-ready data that you can use in your own analysis freely. On the interferometric side of things, ALMA large programs, if you go to this website, you can look at all of the active ALMA large programs. These have an obligation to provide data to the community for your research. Okay, so you can go to this website here and you can see all of those active research programs and identify which of them actually have data that's available for download. Some, not all, telescopes have data repositories or archives. Some are better than others, where you can actually go and download data yourself. The caveat here is you're probably going to be downloading raw data files that you actually have to process yourself to make science ready. And then there are also facilities like the Dataverse, for example, so people are publishing their data along with their publication in the interest of reproducibility, where you can go and you can type in here Herschel, High-Gal survey, and it'll bring up all of the data associated with that, so you can download that and begin to actually analyze that. So these are just some of the places that you can find ancillary data for the science project that you're working on. Personal experience here as well is most people tend to be nice in this field. You can ask them for their data, and if it's not earmarked for a PhD student or a master's student at the time, people are most likely happy to collaborate with you on a particular project, particularly if you've got a good idea. All right, so what are the key metrics, or some of the key metrics that we're going to use to describe the filamentary structure of clouds? This slide is a bit boring, I apologise, but I will make them available. Okay, so the first thing that we're going to look at is the structure itself. So catalogues of sources. This can be cores, this could be the identification of filaments within your data. Kind of riffing on what Mark said earlier, we've got kind of the column densities and how to derive those. Temperatures, this can be just temperatures or gas kinetic temperatures. Masses, which comes from typically from the column density within a predefined contour, depending on where you draw that. Number densities, so actually deriving the density of the structure that you're looking at, assuming some geometry, right, which comes from measuring the size of the structure. So that might be the radius of a spherical object, it could be the width of a filament, or it could be its length, for example. Magnetic field strength, and then also the kinematics, right? So the velocity dispersions, velocity gradients derived from velocity centroids. So these are the kind of key metrics that we're going to extract from our data sets and use that to get at the physics of what's going on. So they're the raw ingredients. What we then want to do is convert these into useful things, right? That provide access to the physics. So in the context of filaments, that might be a metric like the filament line mass, right? So how much mass per unit length is in my filament? It'll become clear why that's a useful metric in just a second. On the kinematic side, what you might want to do is work out the relative importance of non-thermal motions relative to the thermal motion in your cloud, right? So you actually get at the kinematics and look at the sort of energy balance between thermal and non-thermal motions. So for that, you're going to need a molecular line, right? So you're measuring here that this is what you observe, and then you can subtract in quadrature the thermal component of the line, assuming that you have an independent measurement of the gas kinetic temperature. That gives you access to the non-thermal motion, and then you can compare this to a useful metric like the Mach number, for example. It might be something like the radial column density profile, so how extracting the widths of these structures and how they behave, so you can relate that to the physics of how actually filaments may form, so how much compression has gone on and what kind of theory actually predicts the column density, the type of column density profile, so you compare that to your observations. The reason for doing all of that is exactly that we want to relate what we see in our data and what we measure in our data to the physics that is actually controlling the evolution of molecular clouds towards star formation. So a very simple model, for example, for a filament is to assume that it's a cylinder, right? More specifically, one of the very simple models is to assume that it's a hydrostatic isothermal cylinder, so something that exists completely in isolation. I think Amy touched on this earlier where she said, you know, what we want to do here is simplify things, right? We want a simple model that we can use to describe the structures that we're looking at and then see whether or not our observations are anywhere near that. Assuming whether or not such a structure becomes unstable to gravitational collapse and then will actually collapse and form stars, we can look at this by comparing the internal thermal pressure, which comes from the temperature in the gas, to the gravitational potential energy. All right, so you can think of this a bit like a jeans-like analysis, which would be spherical, but just in a cylinder. Okay? The key difference between the cylinder and the jeans-like analysis is that thermal pressure in the cylinder is acting radially, but you've got no compression, you've got no support in the longitudinal direction. And the reason that's important is because this is how we think filaments may actually fragment. So in sort of keeping with the jeans-like instability, you can derive, for example, a jeans length for a cylindrical structure and a jeans mass as well. So how are those fragments going to be spaced, and what are the mass of those fragments that are going to be produced? So the key thing here is what we call this line mass ratio. So this is bringing in this measured line mass. This is why I said this was important. So we can define a critical line mass where the thermal pressure inside the filament is in balance with gravity. Okay? Such that if we take the line mass of the filament that we're looking at and take the ratio of that to the critical line mass, if we have a ratio of less than 1, we call this subcritical. This means that thermal pressure is winning out over gravity. This thing is not going to collapse. If it's above 1, we have a supercritical filament. This is going to collapse radially. All right? As a visualization of that, because this is kind of easier to kind of follow looking at this, this is a very simple simulation of a hydrostatic isothermal cylinder. Time goes on the vertical down the slide, right? So this is the evolution of this cylinder. And here there's two different kind of configurations. So one in which we're actually close to criticality, so thermal pressure and gravity are in balance with one another. what you see here is that the filament is supported radially, but what you see is the density distribution begins to clump up, right? This is that kind of fragmentation. This perhaps is analogous to how we think cores may form within inside these filamentary structures. The flip side of that is this one here, where we have a supercritical filament, right? So the line mass is vastly in excess of the critical line mass, and what you see here is that this filament is collapsing radially, right? The thermal pressure inside the filament can't actually support the cylinder itself. It just collapses into a spindle. This is actually very handy. Good. All right, so that's the kind of the basic metrics. How do we actually extract some of these metrics in practice? Broadly speaking, the techniques that we use to extract useful information from our data can be categorized into kind of two main bins, if you like. So on the one hand, we have feature extraction. So this is where we're actually going to identify the structures in the clouds. These are the filaments, the cores, whatever you want to call them, for example. On the other side, we have pixel statistics, so making no geometrical assumptions, just describing the distribution of our data. So just starting with an example of how you might actually do this in practice. Let's say, for example, you want to measure the distribution of filament widths within a column density map. So what are the steps involved for you to actually go and extract that information? So here on the left, we have a Herschel observation of a molecular cloud. This is actually already a column density map. Mark showed this in his talk this morning. So it's already been pre-processed, right? There's already some assumptions that have gone into producing this image. But let's assume that's our starting data product. It's a column density map. On the right-hand side is a zoom in of this particular region. I'll show you where it is in just a second. And what you see is all these filamentary spines that are overlaid on the data set. So what is actually going on under the hood there is an intermediate step, which may not be that obvious. So this is just the region that's actually zooming in. And that is that these filament finding algorithms are typically not applied directly to our column density map. All right? There's an intermediate step where we're actually processing this image. And that's important because, so in this particular instance, they're using a technique called wavelets. Wavelets allows you to morphologically decompose structure in a data set such that you can identify things that look approximately round versus things that look approximately long and thin. The idea is you're just bringing out the structure so that the filament finding algorithm has an easier job, right? That's one method of doing it. What you might also do is you might, because the cores are very bright, they're very small, what you might do is actually just suppress the brightness so you kind of flatten the image so you bring out the contrast in the connecting structure between those cores. So you apply your filament finding algorithm to this processed 2D image. The next step in the process, the output of that process is a catalog, an index catalog in some form of data structure, also an index map of where these filaments lie on the plane of the sky. Once you have that, you take your catalog of filamentary structures, how many there are, you're going to then divide that filament structure along its primary axis into orthogonal slices. You're then going to take those slices and then you're going to go and apply that to the original column density map, so you get the radial column density profile along each of these individual slices. And then you're going to model that, right? So this is one particular model, but there might be other models that you want to use. And you might be actually describing parametrically either the average column density profile along the filament, or you might be sort of describing the ensemble, so fitting every single one and then describing the ensemble afterwards. On the pixel statistics side, I'll come back to that in a second, you might want to describe the distribution of column density within your clouds. So, or in a series of clouds to see how they vary, see how star-forming clouds differ to non-star-forming clouds, for example. So here you're going to take your column density map, and you're going to generate a histogram of the column densities or a probability density function of the column densities within a contour, and you need to define that contour of how you actually want to do it. And you're going to describe the shape of that distribution, whether that's statistically, so non-parametrically, or parametrically, where you're actually fitting a model, whether that's a log normal, or whether it's a power law, or some combination of the two. And the reason for doing that is so that you can quantitatively compare between different regions to say how one differs to another. Finally, if, for example, your goal is to measure the kinematics, so for example, the relative, if your goal is to measure the non-thermal motion in your cloud, Here we're going to start with a 3D data structure, so we're starting with a data cube, right? Starting with a spectral line data cube. We're going to mask the data first because we don't want our statistics to be completely dominated by the noise in our data. But they're going to compute the moments, and then what you do is you can either estimate, if you have an estimate of the local temperature, you can then decompose the line width into both non-thermal and thermal components, for example. The point of all of this is to say that, looking at what's going on under the hood. So even something as trivial as saying, I would like to understand what the width of my filamentary structures are, has many individual steps that actually go into that. Each one of those steps has associated assumptions, has associated uncertainties, and it's kind of our job to determine what is, the impact of those assumptions on our actual science that we're doing at the end of this. So there's a lot that goes into these measurements. So that's the kind of the practical side of things. What I want to do now is just kind of highlight some of the key takeaway messages, getting on to actually looking at the internal structure. First thing is that filamentary morphology is really ubiquitous in the interstellar medium. First takeaway message. So we see it everywhere, right? So across multiple scales. So it might be galactic scales, so talking about 200 parsec long filamentary structures that appear to delineate galactic structure. It might be getting down to sort of sub-parsec scales and looking at individual, what they call fibers, dense fibers within the interior of molecular clouds. It's also independent of phase. We actually see this in the atomic gas in addition to the molecular gas, okay? Less important in the context of star formation, but again, this kind of, boilerplate term of filament kind of covers across spatial scale and across phase in the ISM as well. Second takeaway is that this filamentary morphology appears to be a natural consequence of many of the different physical mechanisms that are actually at play in the interstellar medium at any one time. So filaments are anisotropic by definition, right? And which suggests that the formation should be affected, if not controlled, by anisotropic agents acting in the interstellar medium. So you've got galactic rotation, you've got shear, you've got supersonic turbulence leading to shocks, magnetic fields, the list goes on and on. This is probably why they're so prevalent on whatever we look at, on whatever scale or in whatever phase we're looking at. So if you take a numerical simulation, perhaps with or without supersonic turbulence, with or without magnetic fields, or with or without self-gravity, or some permutation of those different physical mechanisms in your simulation, the output structure tends to be filamentary. And that is to say that it's then extremely difficult to determine if, for example, there is a dominant mode for filament formation in the interstellar medium, and then link that to how that actually relates to star formation. And I think Rowan Smith said this best in her talk at PP7, where they put together a meta-analysis of different filaments, and they were looking at numerical simulations of filament formation. She said, I'll let you into a secret. Our idea was that we're going to look at all of the different physical mechanisms, and we're going to look at all of the properties of the filaments and look for differences. The sad truth is when we did the analysis, we could not separate them. There was really no difference. So these things are everywhere. They're formed by many, many different physical mechanisms, so how are they important for star formation? Well, the good news is that dense molecular filaments do seem to be an important component of the star formation process. So you can take an image like this. So this is combining our feature extraction methods, but also the pixel statistics. So on the feature extraction side, we're identifying all the filaments here in this particular image, and we're finding all of the protostellar cores and the prestellar cores in this image. In the pixel statistics, we're then looking at column density PDFs. Right? So the blue curve describes the PDF, the column density PDF of the entire image. And what you find when you integrate under that column density PDF to derive the mass is you find that most of the mass of the cloud, so over 75% of the mass of the cloud is actually at low density, right? AVs are somewhere between sort of 3 and 7 visual magnitudes. But what happens is, so the red curve here is actually identifying all those pixels that are associated with the cores and just subtracting them from the main column, from the overall column density distribution. What you see here, this is just a small fraction of actually the mass in your cloud, right? But when you subtract the filaments, above an AV of about 7, a significant amount of the mass, so 50 to 70% of the mass within the cloud is contained within dense filaments above an AV of about 7. right? 50 to 20% of the mass above that density, above that visual extinction that's found within cores. The other thing to mention here is that in nearby clouds, certainly, and the absolute numbers here are going to vary from cloud to cloud, but in nearby clouds, roughly 75% of all prestellar cores are actually located on or near to these filamentary structures that are at high density. So filaments do seem to be an important component of the star formation process, but predicting which filaments will actually progress towards star formation is a tricky business. So while stars do appear to form in molecular filaments, not all molecular filaments are going to form stars. So here's just a visual representation of that. On the left-hand side here, we have the Polaris molecular cloud. On the right-hand side, we have Aquila. You would probably describe the internal structure of both of these as filamentary, right? Here, okay, it looks more wispy, it looks more like cirrus. Here we can see probably there's higher density filaments, but essentially it's filamentary. But the difference is here we've got basically zero star formation going on. And here we have lots of star formation. So how do we actually pick out ones that are going to form stars and ones which aren't? So is it possible to make that prediction? So one metric that people have used is to look at this critical line mass for a hydrostatic isothermal cylinder in these filamentary structures. So casting your mind back, this describes the balance between the internal thermal pressure in the filament and gravity, right? So you have this critical line mass. And what's actually being plotted here is the ratio between the observed line mass in this region, so this is the color scale in these plots, to this critical value. So when it gets up to the white here in both of these images, this ratio is about 1. So above 1 it's supercritical and the filaments are liable to collapse. So what you see comparing and contrasting the two is down here we're nowhere near this kind of critical line mass. So thermal pressure is winning out over gravity. So these filaments aren't collapsing and forming stars. Over here, however, you find this correlation, spatial correlation, between where the stars are actually forming in this cloud and where these filaments are close to this critical value or even supercritical. So, indicating that these filaments would be prone to gravitational collapse. So is this idea of a hydrostatic isothermal cylinder a reasonable approximation to, or a reasonable predictor of where we think filaments are actually going to collapse and form stars? The answer is not simple. So what you're looking at here, this is a meta-analysis of Alvaro Carr's PP7 chapter. So what they did was they took a whole bunch of filaments from the literature. There's about 20,000 filaments in this sample. And they're plotting here the filament mass on the x-axis versus the length of the filament here on the y-axis. So you can see this is spanning 8 orders of magnitude almost in the filament mass and 4 orders of magnitude in the length. So going from up here, several hundred parsecs, so these giant galactic filaments that are tracing galactic structure all the way down to sub-parsec scales. The distribution goes as mass is proportional to length to the half, right? This is actually shallower than this, which is indicating this critical line mass for the hydrostatic isothermal cylinder at 10 Kelvin. So when we look in a bit more detail what we're finding here, so when you have filaments that are less than about a parsec in length, we see that there are many filaments that are actually subcritical, right? So they're leftwards of this line, which is showing you where this critical value is. This is probably telling us that these filaments are roughly transient. They're not going to collapse and form stars, but the distribution is also broad. There's a lot of scatter going on here, and some of these filaments are indeed consistent with where you would say they're about critical. The problem is with this as a predictor is once you get above about 10 parsecs in length, we find filaments that have line masses vastly in excess of this critical value. So if we just take that very simple model of this hydrostatic cylinder, these things would be incredibly susceptible to radial collapse, right? So it begs the question, why would we even see these structures to start off with? So then how do we interpret this plot? What this plot does show is that filaments is an incredibly broad term. We're probably not looking at the same kinds of things at all scales, right? We find filaments within filaments. The structure, the internal structure of molecular clouds is inherently hierarchical. And they're also dynamic structures as well, where their properties and their star formation potential are probably dependent on their environment and the physical scale in which you're actually looking at. So this scaling of the mass going as length to the power of a half may be a consequence of the fact that we have this hierarchical structure. So it can't simply be described by segmentation. So if I have a filament, let's say, of a line mass of 100 solar masses per parsec, if I just divide this up into equal length chunks, the line mass is just going to be the same in each individual chunk, right? It's uniform line mass. That's not what we observe. We observe a shallower distribution here. The reality is that we're looking at structures within structures. And I try to illustrate this. So this is an infrared dark cloud. It's back to that infrared dark cloud that I studied in my PhD. Realize there's not a scale bar on here. This is about 10 parsecs in length. So you can see here at this resolution, which is about half a parsec, you just see a kind of a single filamentary structure. So you might compute a line mass of this and try and actually infer its stability from that information. Yeah?
Can you just go back? I think you lost me on one small thing. So the measurements in this diagram are not independent. There's actually like the same subfilament that exists inside a maternal filament that only appears 2 points on this plot.
Yes and no. They come from different. They can come from different data sets. So that, but yeah. So you've got like a parent filament, might be a low angular resolution observation, and someone's gone observed it. Potentially, there's a whole bunch of different traces that are being used here. There's a lot of observational bias in this, and I actually think the authors of this paper actually do a really good job of discussing that. But they're not always uniform, so it's not always the same data set. Yeah. All right, so this is a 10 parsec filament, which you would just say is a singular filamentary structure. If you zoom in and now observe this at about 0.1 parsec resolution, you actually have, you actually begin to resolve structure within the cloud itself. If you then zoom in again, what you start to see is additional filamentary structures becoming apparent along this kind of main filament. So here we see multiple filaments that appear to converge towards this central region, which is very bright and very dense. If we zoom in again just on this particular region, what we see is that this filamentary structure is actually persisting all the way down to once we've got a resolution of 0.01 parsecs. So we have filaments within filaments, and actually what's happening is the density is increasing as we go down in physical scale. So if you were to take a single filament family, Amy, right, so this is, let's say, this is not an actual filament in this plot, right, this is just me drawing circles on top of this, but right, so you've got, this is your parent filament, let's say. The interpretation here, so the normalization, so where this actually appears, the parent filament in this plot, or where the relationship appears in this plot for an individual family, the normalization depends on the parent filament. The interpretation then is you fragment, right? So you have subfilaments within that structure, and then you have subfilaments within those, following this relationship where the mass goes as the length to the power of a half. So you have, this is different for all individual filaments, so you have something that's here, something that's here, something that might be slightly different in terms of the slope, but in general, so this is kind of what they interpret. It gives you the kind of the scatter in this diagram. Another important plot is the upper and lower point is the upper and lower bounds in a plot like this. Up here, above this dashed red line, is where the UV field, or where the density of the filament is low enough such that the UV radiation can actually dissociate molecular hydrogen. So here we're in the H1 filament regime, right? So less important for star formation. This red line, so down in this part of the plot here, is showing you the virial line mass, right? So this is an extension of this idea of this hydrostatic isothermal cylinder. Now, rather than just including the thermal pressure, it's also including non-thermal motion within the structures as well. What this is telling us is that these structures are dynamic, right? So these filaments or these structures, the internal non-thermal motions within them actually increase as a function of increasing scale, a bit like Larson's relation. So they incorporate in this, and the argument in this particular paper is that this line is approximately tracing the lower bound of this distribution. And so their argument is that what this is probably telling us is that the maximal line mass that a filament can achieve is probably set not just by the thermal pressure, but by the combination of the internal thermal and non-thermal motions as well. The key point here, yeah?
Can I ask? That dissociation line, how exactly was that computed?
I will have to look it up, but it makes a lot of assumptions about them being in isolation and various other bits and pieces, but I can show you where it is.
Okay.
Yeah.
I'm just, it's not obvious to me that you could draw a simple line that way.
Yeah. I'd have to look it up.
Okay.
I'm kind of ignoring it purely because of the fact, so actually, let me just show you quickly while I'm doing this.
And then if you can see what is a non-thermal motion and what is included in that very
That's a fantastic question.
ample.
The reason I'm hiding parts of this plot because for the stuff that we don't actually care about. So these are all the H1 filaments that have been identified. So it's not just simple kind of delineating where you have molecular filaments and where you have H1 filaments. They are actually doing some calculations here. I'm just hiding a part of the plot that is not relevant for star formation, essentially.
Okay.
But I can show you where to find that.
Since you have that up, what's the cyan little cross plus symbol in the middle there that's on the solid
Help me.
line? Up cyan, yeah.
This one. So these are particular.
Yeah, I'm just sitting here read the legend.
So this could be no. Oh yeah, so it is one of these hubs. So hang on a second, I'm spread across multiple screens now.
I just can't resist, sorry.
I have a sneaking suspicion it could be Orion.
Yeah, that's what I'm
Yeah,
asking.
it's the ISF. Yeah, exactly. All right, this slide's getting a little rubbish, but whatever. Okay. The question, non-thermal motion, is an excellent one. It is a broad brushstrokes term to incorporate everything that is not thermal motion, right? There's no way we can actually establish this from our observations. It's often inferred as turbulence, right? But that could actually include infall motion, it could include longitudinal collapse. We don't have a way of easily delineating that from our observations.
Is viscosity included? Viscosity of the gas, I suppose, would be an important, because I was always wondered about filament structure. Structure indicates a laminar flow, so it's a low velocity. So through velocity kinematic information, you would be able to understand what's happening there or not. I don't know. It's just.
It's very difficult, right? Because we
filament
have
is low velocities. It's true, no? Inside the filament, it's low velocities.
Yes,
And
but there is a
so it's
dependency on scale.
dominated flux.
There is a dependency on scale, right? So the kind of the Mach number will increase as a function of size scale, much like a Larson's relation. So when you're down at, say, less than half a parsec in physical scale, you're basically at sonic scales. In terms of the velocity dispersion. Above that, you very rapidly get into the supersonic regime where the velocities actually can be quite high, particularly when you get the large scales. No, not necessarily, but this is the question. This is what it's arguably why do we actually see those structures under those conditions? Yeah, but it is a broad brushstrokes term that incorporates everything that's not thermal motion. It's very difficult to actually establish what that is physically. So there's an interesting point here that's actually related to this red curve in terms of the non-thermal motion here. So this is making an assumption that that non-thermal motion is acting as a pressure in the same way that, for example, thermal pressure would. But if it's not true, there's no indication that turbulence actually acts as a pressure in the same way, right? And it's also not necessarily even turbulence as well. So there's a kind of there's a hand-wavy argument there as to try and understand why we actually see these filaments that we otherwise think would be incredibly gravitationally unstable and we just shouldn't see them. The final thing that I wanted to make here is that unlike this kind of very idealized hydrostatic isothermal cylinder model, filaments do not exist in isolation, right? They accrete from their surroundings and they feed their internal cores. So this is an example going to the velocity structure, so looking at the kinematics. Amy, I added this because you asked me if I was going to show the kinematics, right? So two different filaments, one that has reasonably simple structure, and then a kind of network of filaments which has this incredibly complex physical structure as well. The color scale in each of these maps is the velocity, right? So kind of the thing that you want to look at is that we see these transverse velocity gradients across these filamentary structures. So here and here, for example, and this has been interpreted as evidence that you've got an ongoing accretion flow onto the filaments themselves. So one way to perhaps actually interpret this plot is that you have like evolution within this diagram. These filaments are not static, they're ever evolving. So This key here gives you an indication of how filaments may move under different physical processes that are actually going on in the cloud. So if they accrete material, they're gaining mass, they move rightwards in this plot. If they're destroyed or they're stretched or sheared out, they would move to the left. Fragmentation is interpreted as moving down here to this, using this m to the power, proportional to L to the power of a half. And so the way that they interpret this is you start with a filament, your parent filament up here, you have this fragmentation, and then you have mass accretion which moves these filaments over here to a point where you actually exceed this critical line mass and you can collapse and form stars. So these are the kind of the takeaway messages, and hopefully there's time for questions, but the kind of the key takeaway messages are that filamentary morphology is ubiquitous in the ISM. Yeah?
Question over here.
I can wait until you're done.
Oh, okay.
Yeah.
All right. They're a natural consequence of many of the different physical processes that are at play in the interstellar medium. Dense filaments do seem to be an important part of the star formation process, but actually understanding which filaments will progress towards star formation is not actually that easy, particularly once you get to the high mass end, where we have these extremely high line mass filaments. But they're not a unique or homogeneous population. There are filaments within filaments. The internal structure of these clouds is hierarchical. But also these filaments are dynamic, right? They're not sitting in isolation. They are simultaneously accreting from their environment and feeding their embedded core populations. And I will stop there and I'll take any questions that you might have. Yeah. Thank you.
This is running around and throw it at.
Max Newman, Rutgers University. I probably missed the explanation, but those blue triangles that sat below the red curve in any of these plots, right? There's like, there are some red circles that are drawn on here that are filaments, I imagine, right?
Yeah.
And then some of them scatter below this line. What was the explanation?
Right. Each of these are different filament families that broadly correspond to, let's go back here, this image here. So what they've done is they've basically taken a bunch of filaments identified in the literature and they've kind of pigeonholed them into different filamentary families. So you've got extremely large things, right, galactic scale filaments, they've taken various surveys there. They've taken at the opposite end of the scale, things like these fiber structures, so filaments within filaments. And that's what the different colors and the different, do you know what, let's just get rid of the things that I've hidden. Right, okay, so you've got all of these different filament families here. So there's no uniform particular type of structure that's sitting below this red curve. Mm-hmm. The argument is that this red curve is not necessarily, it's not fit to the data, right? So they're just looking at the virial line mass under certain conditions, and they are looking at how the non-thermal motion actually scales with size. But they do say the absolute position of this red line will move depending on, for example, where you kind of draw those things. So they're saying it roughly kind of traces the lower envelope here, and that is probably what sets the maximum possible line mass. But obviously there are structures that sit below it. So for example, these things here are what we call, I didn't go into this, but perhaps I should have done. So these are kind of hood filament systems. They're kind of extreme objects where you have multiple filaments that are actually feeding a central potential well. This is kind of one of the pathways that we think that filaments may be important for the formation of high mass stars. So these are almost kind of unique, but kind of extreme objects in the distribution. They sit kind of outside of the scatter, basically.
So it's not just normalization, it's their extreme system.
Yeah.
Thank you.
Yeah, it's two questions actually. So the first one is, in your interpretation plot, the last one, did the authors check, or is it known if the filaments to the right tend to be more protostellar? Because especially the ones that are significantly to the right of the virial line, if they are richer in stellar population, and the ones on the left tend to be more like primeval, no?
Yeah, so it's not that simple because, so they're using this as a way as to describe some of the scatter, right? So just taking a backward step, they've done their best to find like a homogenization of the data that's actually going into this, but of course there are a lot of uncertainties that go into this. So there's distance uncertainties, there's algorithmic uncertainties and various, so some of the scatter is going to be caused by that. They're using this up here in particular as a way as to say how filaments may actually move and evolve throughout this plane. It's kind of why you have such a broad distribution, why you've got so much scatter. So for example, if you have this particular line here, you might also have a filament family that's here, so just sort of shifting it in this direction, depending on what the kind of, they argue that the point at which these filaments become susceptible to collapse is related to the accretion timescale, and also the timescale for gravitational collapse. That does actually divide this this plane into sort of two regions. So down here, where fragmentation becomes important, and up here where accretion is important. But that depends on what the structure is that you're looking at. So it kind of, that line moves as to where it's actually critical. So it's not as obvious as saying if something's here, are these ones all the ones that are forming stars, and then are these ones not forming stars? Because it depends on the initial normalization, which they're only set by the parent filament.
Yeah, the other thing, this thing is sort of assuming that all filaments have the same aspect ratio, no? So if you have the same filament and it becomes more roundish, say the same mass content and it becomes more roundish, it moves to the right, no? So right, okay, so it's somehow considered, okay, thanks.
Michael Lowe from the University of St Andrews. So firstly, just looking at this, is there any sort of, beyond just that some of the data has been cut off, reason that there is more scatter on this virial end than there is on the H1 end? Like, just that it seems like such a sharp cutoff just to look at. Is there a physical reason for that, or?
So why, for example, were they all contained down here, and for example, not filling this segment in this direction?
Yeah, just like that.
That is probably an observational bias.
Okay.
Right, so it's probably coming from a singular survey, which is susceptible to, which has found a particular type of structure in the H1, and there aren't many surveys probably looking at population statistics of H1 filaments, so that's probably a reason for that. Yeah, it's probably a bias.
Matilde Fernandez from IAA. I would like to know if it's possible to connect what these filaments you have been talking about, and especially the gores that one start to see, with the timeline that was shown previously with the 25 kilo years, then the 0.15 mega years, protostar lifetimes, yeah. So I guess this is at the very beginning, so very far to the left, but because, in fact, the question is also, what's the starting point of this timeline? So is it possible to say?
I think it's more fluid than that, right? And so actually sort of saying where T0 is actually quite difficult. A lot of these things are actually happening simultaneously. I think probably one of the main things to take away from this is these filaments are not static, right? They're evolving, they're turbulent, and so you get kind of fragmentation along those structures at different points in the evolution of this, of these structures. There probably is a connection though via, so the argument that they make in this paper is you've got this accretion timescale, right? This is in competition with the timescale it takes for the filament to actually fragment. So they say at the point at which the fragmentation timescale becomes smaller than the accretion timescale, that's where you're going to get the fragmentation. That then probably leads in as a quasi T0 for maybe the kind of the protostellar evolution, but because once you've started to collapse and fragment, right, these things are then gravitational.
I would also just add that there is no initial condition that doesn't exist. T equals 0 doesn't exist in the ISM.
It's not like this thing is happening, then it...
T equals 0.
Yeah.
The clouds are evolving from less than structure, more than collapsing, blah, 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 rejecting, blah, blah, blah. And so the concept of T equals 0 or in the initial conditions already has some significant flaws.
And very short question. is it possible to also form stars without filaments?
Yeah, I would absolutely. So something like B68, for example, doesn't appear to be, I mean, it does have extended structure around it. Well, okay, it depends how you look at it, right?
It's interesting, if you look at the photographic plates, you can see it looks like a series of like broken cords that you could draw a line through, almost like a maternal filament broke up.
Yeah.
But B335 has no such structure, it's just out there in the middle of nowhere.
I guess the key point here is just that, you know, the majority of molecular clouds appear to have this this filamentary structure, and so things forming in isolation, just kind of sitting around and not doing anything apart, this is probably the exception to the rule rather than the rule itself.
All right, I think we'll make this the last question.
Hi, Victor from London University. I don't know how to ask this because it's a vague idea, but for example, if you want to quantify the superstructure of filament, like the number of little filaments that are inside your main one, is there a way to do that and how that could affect in the net angular momentum? Because I'm thinking about the galaxy formation and the way that you have a large scale structure that is a filament that is feeding the galaxy, for example, or system like inside the disk scale that also can have filament structure. So I don't know how.
It's a good question. I think the first part is easier to answer than the second part. So the way in which it is done is typically at different resolution observations, right? So for example, the filament that I showed in the very first slide, right, this filament in Taurus, for a long time it was investigated as a kind of prototypical singular filamentary structure, right? And analysing that in the context of star formation. It wasn't until more recently when higher angular resolution observations became available that you could actually break that structure up into a series of kind of entwined filaments that go along the length of that individual structure. So you can look at that and that's precisely what they're doing here in terms of these kind of scaling relationships, so quantifying the number of those structures that you can identify. Of course, there's observational bias there because you're looking at a particular molecular line, say, and you'll have a particular sensitivity and those kind of things. But that's essentially what's being done here. So the torus, that kind of prototypical filament, initially, you would have observed it down here, but then you're observing a population of fibers once you get down to this kind of scale down here. But of course, there's observational biases in there as well. The second part of your question, you're going to have to repeat. It was about the angular momentum, right? But I don't know.
Yeah. So if you have a filament that is very divided in very short filaments, small filaments, and you want to quantify the net angular momentum, I don't know if at some point you are not going to have like probably you are comparing with the plane of a disk of a galaxy, and you want to know if it's parallel or perpendicular, and you have a filament that is very divided in a little superstructure. I don't know if your angular momentum is going to be very affected because you have like a lot of structure pointing in a very different ways than like if you only have like a very big filament going through thinly to the disk.
Okay. Mark is hovering, but I will try. So in terms of the relative orientation of these filamentary structures, right? So on the largest scales, a lot of these large filaments in particular, which are delineating galactic structure, tend to be in the plane, right? There are studies that have looked at the orientation of filaments in H1, for example, where you do see examples of filaments that are orientated perpendicular to the plane. So this is a paper by Juan, and he attributes that structure to feedback, basically. So when you see these filaments that are actually perpendicular to the plane, they're typically associated with locations of high mass star formation feedback. When you get to smaller scales, you tend to find that most of these subfilaments are elongated, kind of following the primary axis of the parent filament. And this has actually been used as one of the arguments as to how these structures are formed, in the sense that they think it's kind of a fragmentation of the larger structure, as opposed to something else. The other way that you can potentially do it, for example, is you form your little filaments first, and then you have a kind of a net flow that kind of sweeps them all up together and kind of bundles them up into a structure that looks singular, right? But that might have, depending on the flow, of course, but it might have more implications for the orientation of the individual subfilaments. I don't think that answers your question, but maybe we can talk about it more afterwards, but that just kind of some insight as to how these things are actually orientated relative to their parent structures.
Thanks.
All right, I think we will have to stop there and move on to the next speaker. So let's thank Johnny again. All right. Continuing my introductions, this is Nora.
Thank you very much. So, indeed, my name is Nuria and I come from the University of Vienna. And this is the first of the two talks that I will be giving this afternoon. So, it's already afternoon. I know that you are also maybe a bit tired. This is the same for me. So I would highly appreciate if everyone joins me in asking questions or enriching the discussion, especially because so the two talks are going to be very much related. First, I'm going to talk about cluster formation and evolution. The second one is going to be clusters and associations in the Milky Way. So very much related, and especially on the first one, cluster formation and evolution. I'm not sure this is necessarily my main expertise. So I will try to give a bit of an observational overview, very much biased to my current knowledge, but especially towards the end, I would very much appreciate if other people, and I'm sure that many of you know much more on this topic than myself. So, okay, then let me directly start, and this is a bit the overview for this first part of the lecture. I will be talking about first cluster formation and then cluster evolution. And when talking about cluster formation, I will be referring to these two particular star-forming regions in the solar neighborhood. And then in the second part, I will be moving to discussing how clusters evolve and slowly disperse into the galaxy. And then we will talk about tidal tails and coronas of clusters. And towards the end, I was planning to profit the chance that I'm talking today to also briefly mention a paper that I published last week, and it's very much related to a question that just happened a moment before. So this was not planned, but I will profit this also to introduce these final results. Okay, so. Already starting, so also I plan to, during the talk, try to open a bit the debate for questions, and I will already start with a very debated topic. So how do we define star clusters? So I'm going to give my own definition. So for me, whenever I talk about cluster, I refer to an overdensity of stars. I don't care whether they are gravitationally bound or not. I just call cluster whenever this is this overdensity of coeval stars, in fact, I should say. And this is very much related to my observational background, because whenever we see a cluster, we just see that there is this population of stars that share a common origin. So when we plot the color magnitude diagram, we see that they align into an isochron. We see that they share the same motions across the galaxy, so we know that they are a family, but we don't immediately know whether they are gravitationally bound or not. For this, we need the masses, which are rather complicated, and this is not immediately possible to know. Okay, so moving on to the first part, so I'm going to show already a few pictures that you have already seen today, but I think it's good. It's just slightly different perspective. I will start with this first introduction, but most of the talk is going to be on the optical. So this is an image of the Orion star-forming region. It is one of the most well-known star-forming regions in the solar neighborhood. This is a distance of only 400 parsecs, and in this area there are several populations of stars which ages between stars that are still on the process of formation up to stars that are already completely formed and even slightly evolved. Then I would also like to start this historical overview with one of the first works in the 90s that showed that stars indeed form in clusters. So essentially in this paper what they saw is that the emission from the gas correlated spatially very well with the position of young stellar objects. And so this made these authors believe that stars form in these clustered environments that are surrounded by gas and dust. So, and this is another image zooming in at the Orion sword, sorry, and this is something that also has discussed this morning. So we are seeing in these pictures how high and low mass stars indeed form together, and we cannot tell and study them apart. So in this area we see many massive stars that are very embedded in this nebula, and the brightness of these stars is what is illuminating all these nebulosities, while here above we see this filamentary structure that contains lower mass protostars. We have just seen now that stars form in filaments, so I will pass very briefly with this slide. This was also only to illustrate that stars not only form in clustered environments, but also in filamentary structures. But I think after the lecture that preceded me, this is already discussed. So continuing with this initial overview, so here we are seeing another image of Orion, first in the optical, where we see all these nebulosities and where all this gas and dust is hindering us from identifying the young stars in this area, whilst the advantage of going to infrared observations is that then we can see through partially this gas and dust. And for instance, in this area where here we are almost completely blind, here we can begin to observe all the young stars that are embedded in this area, and same would happen here and here. And for completeness, this region has also very recently been observed with the GWST, with a much better resolution and sensitivity, so the number of stars count that we will be able to obtain from these new images are going to be much better than what they used to be in the past. So continuing with this area, now this is an image obtained with the Spitzer telescope, and here in this image, this was obtained analyzing this image. And so in principle, these authors, what they found is, or they distinguish between two different populations. So the red ones, they are protostars, and the young stars with this are indicated by these green markers. And for some time it was debated whether there were these two modes of star formation, some stars which form in a much clustered environment, while others would form in these sort of diffuse populations, more sparse populations. And some simulations show, and I would argue that in fact, probably all the stars form in very clustered environments, and only later, once they are formed and begin to evolve, they begin to escape from these very clustered star forming regions, and they begin to populate these more diffuse areas. So then it's very important to know precisely the age of the population of stars that we are investigating or studying in order to tell apart whether if actually these stars form in very sparse and diffuse areas, or on the contrary, they form clustered and only later they move away from the places where they were actually born. Okay, so this is what I wanted to say about Orion. So now I'm going to move to the other main star-forming region in the solar neighborhood. And for that, I will briefly introduce the Gaia satellite. I think this should be much known for everyone here, but maybe because there is people working in different wavelengths, just Gaia is a satellite that is obtaining a whole sky view of our galaxy, and this is the image that we have from Gaia. But in fact, this is not an image. This is important to remind everyone that what we are seeing in this map are star counts. So essentially, when we see an area very bright, it means that Gaia is observing a lot of stars in this area. There is a high density of stars, while dark areas have low densities of stars. And this is what we are seeing here. So in the galactic plane, we see all these dust extinction. So essentially, then Gaia is not able to observe anything that is at the back, also because Gaia is observing in the optical, where we just said that there is a lot of extinction. And okay, so and then this is what we observe with Gaia. And so now in this region, we can already see this second region I wanted to mention. This is the Scorpio-Centaurus OB association, is exactly in this area that I'm indicated with this red circle, but I'm not sure if everyone sees already immediately Scorpio-Centaurus. No? No? Okay. Could be anywhere. So indeed, and the answer, so this is a work that we led from the University of Vienna, and so we were able to identify all these clusters that populate Scorpio-Centaurus thanks to the excellent astrometry of Gaia, combined with machine learning techniques. This was a work led by Sebastian Ratzenberg, and he developed this Sigma algorithm that is specially designed to, sorry, I mispronounced probably the name. So this is especially designed to work in very nearby star-forming regions where the projection effects are very large. So, especially because these regions cluster best in 6 dimensions, but the radial velocities of Gaia are usually not at the same level of the tangential motions that we have with proper motions and parallaxes. So it's important also to have techniques that are able to cluster in 5D instead of 6D. So this is a zoom in into this region, and where we have indicated these 3 main areas. These are the historical associations in Scorpio Centaurus. So we have Upper Scorpius, Upper Centaurus lupus, and Lower Centaurus groups. And classically, so it was thought that this area is the oldest, and at the edges we have somehow younger populations, but now we see that in fact each of these big groups is made out of many different clusters. You had a question? Yes?
How do I use the mic?
Martin, throw the microphone, please.
He's getting both chocolate and the microphone. I'm double fisting.
Max and Rutgers. How separated, so these were made using Gaia 60's motions?
5D. So it's 3D positions plus 2D tangential motions.
Okay. And so, I don't know, did you already say what the color coding was? Or did I miss that?
Okay, so here it's to try to highlight the different groups. So every color is a different group, but here they don't yet correlate with any other magnitude. In the same image, they will.
Got it, thanks.
Just one question. Have you tried for radial velocity, for example, to complete this? The Gaia ISO survey, they have high resolution spectra. They could provide some additional information to this tangential velocity.
So
have you used this?
We didn't use this information.
High resolution.
We didn't use this information for the search because using these spectroscopic surveys automatically reduces a lot the number of stars for which we have. We are using this, so now that we have this sample, indeed we are cross-matching this with other surveys for follow-up studies, and I will show also some of these.
I think some of the other papers you're citing there, I mean, certainly the Zergel one, which I'm on, does use 60 with the radial velocity information. But yes, the trade-off is then you have much smaller sample size.
Yes, of course. We're used to 500 or something.
It's better than that, but it's, it means that you have, thousands rather than, millions.
Yes.
Yeah. Maybe I should also add that, so this is the work that Sebastian did. I did another work only focused on Upper Scorpius in 60, and the results that we come up are in the end quite similar for most of the groups. So I think that is also a nice confirmation. And also some of these other students also focused in some parts of this area, and for the big clusters at least we more or less agree. So I think this is a good confirmation that using different data sets and different algorithm and clustering techniques, we in the end come up again with some differences, but
so you would say that it's not necessary to use radial velocity high precision?
No, I wouldn't say this.
Because if there's a good correlation, so maybe you found any index which actually indicates some,
Yeah, I mean...
If there's a good match, that's my question.
Yes, I mean...
How do you judge this match?
Especially, I think this becomes more and more important when you try to come to closer and closer regions. Because then the projection effects become even stronger, so it's even more important to cluster in 60. Maybe this is at the limits where 5D is working okay. We are now currently working on some even closer clusterings, and there it becomes really crucial to do the clustering in 60. But obviously, even here, if you have the 6D information, you will do better. This is always for sure. Yeah. Okay, so yeah, this is the clustering that we obtain in 5D, and then what we try to do is obtain a color magnitude diagram for each of these clusters, and now they are the exact same clusters, but colored by age, where oldest clusters of around 20 million years are in red, and young clusters of around 5 to 3 million years are these blue ones. And the first, I think, striking feature of this diagram is that the oldest clusters seem to be placed at the center of Scosen, where we observe these coherent patterns where clusters are slightly older every time, and the youngest stars are placed exactly at the edges of Scosen. So this is highlighting these three changes that we identify in this region. We call them the Corona Australis chain, the LCC chain, and the upper Scorpius chain. And again, we are going to see the same information in a slightly different visualization. Now, we have selected the 5 key snapshots in this diagram, and at each time we show the stars that are being born at that time. And again, we see first clusters are born at around 20 million years ago at the center. 15 million years ago is where most of the stars are formed in these big clusters that contain most of massive stars in Scocen. And later, around 10 million years ago is when this change developed, and we believe that these very well-defined patterns maybe are telling us that, so maybe these are a result of the feedback, stellar feedback of these earlier populations. And finally, what we see is at the edges of this change, there is still ongoing star formation. And this is true for the 3 chains. Here you don't see the one on Corona Australis, and this is only because the youngest population in Corona Australis is still very embedded into the parent cloud, so this, the young stellar objects in Corona Australis are not observed with Gaia. One should go to the infrared to detect them. And maybe also another note on one of these chains, Corona Australis, where here we have used the 6D phase space to analyze this chain in a bit more detail. And so essentially what we try to look is how the velocity and the position diagram looks like for the clusters in this area. And essentially what we see is that clusters farther away from the galactic plane, so this is where the galactic plane sits. These are stars above the galactic plane, and these are stars below the galactic plane. And what we see is that stars below the galactic plane are moving with the highest velocity style down from the plane, and this is in principle the opposite of what you expect from the galactic potential. So if you have stars in the galactic potential that are not affected by any external force, these do a vertical harmonic oscillation. So when you are very below the galactic plane, essentially your velocity is very close to 0, and at a point it starts going up. And this is exactly the opposite of what we are seeing here, and the way we interpret this is another proof that these generations of stars have been pushed and triggered from the feedback of previous generations. And this is work that was led by Laura Posch, that was a previous student of this school. So I have showed you on a couple of examples where stars form in clusters in different regions, and this is true for very different masses. This is the cluster mass function, and essentially we know that stars form in clusters at very different mass regimes, at very different environments, and this is only telling us that the most common output of clusters are rather low mass clusters that probably are going to be gravitationally unbound and are going to naturally disperse into the galaxy. And this is, we are now slowly transitioning to the second part of the talk, where we will be talking about how clusters disperse into the galaxy. And this is the result of some simulations where we are seeing the velocity map of clusters at different ages. And what we see is when stars are very young, when clusters are young, they are very easily detected in these velocity maps. So it's very easy to distinguish the different clusters, and while they evolve, if they are not gravitationally bound, they slowly smooth and disperse, and so this becomes more and more complicated to identify older clusters. And then the way, how do we search for these older clusters or for very extended members of the cluster? So again, ideally, one would cluster in 6 dimensions, and when this is not possible, then we need algorithms that help us to go beyond this limitation. And now this is also possible thanks to the excellent precisions of Gaia. This was probably not possible in the past due to the larger observational uncertainties. And soon after the second release of Gaia, 2 independent groups came to the same result and observed for the first time these long tails in the famous IRS cluster. And also around the same period, it is when it was discovered the first streams in the solar neighborhood. And in this case, by streams, I mean these very elongated structures, clusters that seem to be already, or that are in fact already dissolving into the cluster. And I think this one is particularly interesting for the age that it has. So it has an age very similar to the Pleiades, and yet the configuration is very different. So I think this is an excellent example to study how different clusters disperse and evolve into the galaxy. So here I'm showing a one-to-one comparison between the Pleiades and this main gas, or this is Eridanus stream. We see that in fact the properties of these 2 clusters are very similar. The masses are more or less the same, they have a similar age, and the main difference is the current configuration of these clusters. The Pleiades is still very, or rather compact in a core. It is, most of the members are still in this core, while this stream is already very elongated. It occupies a space of over 400 parsecs in the galaxy. So again, thanks to Gaia, it has been possible to investigate, to find more and more these sort of structures, but it's very important to open the search boxes that we use. And here I'm just going to illustrate this with one example. Here we are looking into the same region at different different zoom-ins. And this is the members of one of the very famous papers for clusters using Gaia data, the papers from Tristan Cantaltodan. And essentially, Tristan was one of the first ones to search, to find many more clusters with Gaia, but he was really focused on the cores of the clusters. Then we do identify on these clusters, but often we are missing most of the stars that are in the tails. So the ones that are already dissipating, and those are very important if we want to study how stars disperse into the galaxy. So this, I showed this example for one particular cluster, but this is now done with some other clusters in the solar vicinity where we have the best precisions. And I should say also that these are in not that old clusters. So already at a few hundreds of million years, we see that these clusters begin to have very extended tails or coronas, however you want to call it. These are the same clusters, and the sizes that we currently know or that they have is of the order of these 100 parsecs. We know that they are coeval because when we plot them in color magnitude diagrams, we see that they all sit into the same isochron. We know that they are comoving. This is in fact how we identify them, again clustering in 5D. And whenever we have the radial velocities, then this is used for confirmation. We also know that these coronas are gravitationally unbound, so the core of the cluster might be bound, but not the corona, and this is how they are expanding, why they are expanding and dispersing. And the origin and the reason why these tails and coronas exist is probably a combination of birth conditions and cluster evolution. So for sure, while as we let the cluster more time to evolve, it will develop slowly these tails and will begin to lose clusters into the galaxy. But we saw this example comparing the Pleiades and this megas stream, and these in fact are at the same evolutionary state. So probably also there is something about the initial conditions on how these clusters are born that triggers one evolution, or so a more rapid dispersion or a slower one. And this is just to illustrate that now with Gaia it's every time easier to identify these type of stream-like features. And with this I will move to the last block of my first talk, which is a new perspective into cluster form. Yeah, sorry.
Ask more questions, get more chocolate. Fairly obvious incentive structure here, people.
Do you know the clusters that appear to have like longer tails? Have you been able to, I don't know, run very simple tests where you like run them back in time with the 5D motions that you have, and see if their birth location effect has a correlation with how elongated they are in the present day? I don't know if that makes sense, but.
I think this makes absolute sense, but there are a few drawbacks here. So first is that we don't have the 6D for all these clusters, right? So we can only do this information for the ones which we have precise radial velocities. The second limitation is related to this first one, and is what is the precision that we have in radial velocities. So these clusters are young, but some of them have hundreds of million years. So going back in time, that much time with a reliable precision, I'm not sure it is feasible yet. Yes.
So, I think it would be quite nice later in the discussion at some place to come up with some kind of working definition for a cluster. Because I'm completely confused now, because I remember Lada and Lada all starts from a cluster, about 80%. Then of course that got wiped away after Herschel. Then I remember Diederik was very good about it. He said, cluster is just stuff that stays gravitationally bound, which is nothing, which is like 5 to 10% or a few. Now of course you are spinning my head around with mentioning clusters all the time, which is for me a coeval kinematic whatever thing of group. So quite interesting, because it's so like Herschel took the cluster, Lada gave us the clusters, kind of. Herschel took them away, and now Gaia is bringing them back, but in a sausage form.
Yeah.
So that would be quite. I don't know whether that's even necessary. I mean, it's kind of naturally clear what we're talking about, but. I don't know, does the field run into the problem of we don't have really a definition of what a cluster is?
Yeah, in fact, I agree with you. This is why I started my presentation trying to at least say what is for me a cluster. I know it might not be the same for different peoples, but I think what Gaia is showing us is that this is a continuous definition. So maybe before Gaia you used to see really compact things that is evidently gravitationally bound, while another very loose association with it's obviously gravitationally unbound, but I think we are starting to see things that are in between, or things that maybe begin as bound entities and slowly dissipate, or maybe even the cluster might be bound but not the outer layers. So I don't think it's clear how to...
Maybe I can help.
Yeah.
I worked with Sassi several. So actually, the idea is that they were bound gravitationally in the moments. Most of them.
While the gas was there.
Yes, everything was there, because actually you have the 6D space, you have the coordinates and you have the velocities in the 3D. So you actually can make convergence algorithms to see where these guys all come from. So you will eventually get into a very packed regions which are gravitationally bound. So right now, evolutionarily speaking, I suppose that actually most of them, they are loose associations and they are not anymore. I would say this. I don't know if I'm saying anything wrong.
Yeah, I mean, I would disagree that they could all be gravitationally bound at the beginning. Again, they could be bound by the gas. The stars couldn't be bound, just because otherwise you can't explain why you come back 100 million years later and, 5% of them are in bound clusters. I guess the position we took in our review is that avoid the issue, don't say stars are born in clusters, they aren't. Stars are born clustered, meaning that the density is much higher than the density in the field. Is this a star cluster? I mean, you look at young ages, and if you do quantitative metrics, like the nearest neighbor distance, right? At young ages, it's a power law, right? This was one of the main arguments against Lada and Lada, is that the distribution of nearest neighbor distances or things like that's a power law. So where exactly did you want to draw the line on this totally featureless structure and say, this is the density that counts as a cluster? Right, there's no right choice for that. It's utterly meaningless to try. And so you simply say, well, there's a power law distribution. Most stars are at a density much higher than the field, but there's no break that would let you naturally define this cluster ends here and this is cluster, this isn't. That is something that happens much later over the course of evolution.
Matilde Fernandez, I wanted to add something here because I come from star formation, long mass star formation, and we were at some point studying some star forming regions like lupus, for example. I'm going to give this as an example with ROSAT data. So these are X-ray observations that what happened was that they found a lot of other young stars, T-Tauri stars, weak-line T-Tauri stars that would emit also an important amount in the X-rays, and that's why they were detected with ROSAT. And the surprise was that, for example, lupus, you have the three, I think, clouds, the three parts in which the classical T-Tauri stars, the ones with the accretion disks, they were like confined in some parts, and then you had an extended population of stars that were the weak-line T-Tauri stars, and later it was found that there were molecular clouds or pieces of molecular clouds in these regions. So I would say that from the very beginning you are going to have at least these kind of regions like lupus, parts with higher density, with more stars, but you also have from the beginning extended population. That probably as the whole thing moves, they will move differently.
Yeah, okay, so I really am not going to add more on the debate because I don't think I already gave my position. Then what I will do is finish my presentation with these last slides. And this is, so this might seem at the beginning a bit unrelated to what I was discussing so far, but I think hopefully this will link soon with the rest of the talk. So I am illustrating this last part of the talk with this nice painting from Dali, because I will be talking about different techniques of measuring stellar ages, and looking at this painting inspired me very much in preparing the presentations of this work, because each of these clocks reminds me of a different technique of measuring stellar ages, each with its own shape, it's using its own methodology, its own models, its own observations, and in the end, let's see if they get to the same time or not. So there are many different techniques of measuring stellar ages. I'm just going to mention two main ones which belong to two different blocks. One, I'm sure everyone is very familiar here. This is isochron fitting. Essentially, you are trying to fit an evolutionary model to the photometry, for instance, of Gaia. So fine, this gives you an age that is somehow related to the model that you use, so it has some uncertainties, but it's really easy to produce, and now we have these isochronal ages for hundreds and hundreds of clusters. The second one is using kinematics, so this has the great advantage that it's completely independent from evolutionary models. But here the drawback is that you need first 6D space phase information, so you need precise radial velocities. And second, you obtain this for young and nearby clusters because otherwise the orbits of individual stars that you are going to compute are not accurate enough. So here the idea is that you take the 3D positions of all the stars members of your cluster and you compute the orbits back in time and try to find the moment when the stars were most concentrated. And for us, this is going to be the dynamical traceback age, so the time where this cluster was most compact. So thanks to Gaia, so these kinematic ages have existed since long ago, but the precisions in the velocity were classically not enough for this accurate traceback analysis. But thanks to Gaia and complementary spectroscopic surveys like Gaia ISO, like Apogee, this is starting to change, and now we have very precise radial velocities also for many stars. So what I did is try to profit these new kinematic ages, these new dynamical traceback ages, and I compared them with ages from isochron fitting. And I think this is immediately clear. I did this for 6 different regions, and it's immediately clear that dynamical traceback ages are still sometime younger, few million years younger than isochronal ages. And we can visualize exactly the same information in a different representation space, where now in the y-axis I'm showing the difference between isochronal ages and dynamical traceback ages. And these dynamical traceback ages always seem to be these around 5 million years younger than ages from evolutionary models. This is true regardless of this, if you want, large scatter that we have. This is because we compared for each of the clusters, we compared our dynamical traceback age to different isochronal ages that we found in the literature, using slightly different samples, using sometimes different models or fitting techniques. And this is also true regardless of, so we did mock simulation to try to estimate the bias of our kinematic ages due to the uncertainties on the radial velocities. And with all these tests, what we were seeing is that still there is a gap between these isochronal ages and the dynamical traceback ages. So this was puzzling me for quite a while, until we convinced ourselves that, in fact, maybe if this is really not related to observational uncertainties, what we are seeing here is that the two different techniques are measuring two slightly different things. So, and here comes the question, so what is the time zero of each of these techniques or each of these clocks? So I agree that the initial age of evolutionary models and isochrons might be not perfectly defined, depending if you want to consider the time when this becomes a class 0, class 1. So I don't know, but because in the end all these processes are very rapidly, for me the isochronal fitting model, so the isochronal ages are telling you is the time essentially when stars have accreted the majority of the gas and become prime sequence stars. And this is going to be still in the uncertainty of less than million year time. So I think it's more or less fine to define it like this. While the dynamical clock what it's telling us, and define it as I have in the beginning, is telling you the time when a group of stars begins to expand and disperse into the galaxy. And these two clocks may not, in fact, measure the same time if this cluster was embedded into the parent gas for a few million years, and this is what we define as this delta H. So for us, the difference between these dynamical traceback ages and ages from isochronal ages is related to the time in which stars were still gravitationally bound due to the presence of the parent molecular cloud. And then the last thing that we did in this article that we published last week is try to see how this delta H, this difference, changes as a function of environment. So ideally we would like to test the mass or other properties more meaningful for the clusters, but those are more complicated to obtain. So let's start with the easy case, which is the number of members per cluster. And despite the still low number statistics, if you want, and the still large error bars in this plot, so we seem to find this trend that is suggesting that more massive clusters, more rich clusters, have smaller delta H, smaller differences than lower mass clusters. And the way we interpret this result is maybe this is caused by stellar feedback. So massive clusters also form more massive stars that maybe disperse the cloud and the gas more rapidly. And then these stars are free to expand at early stages than lower mass clusters. And so this is only a cartoon to illustrate the main result of this article that we published last week. And with this, I will finish with my summary and hopefully ideas and topics for discussion.
Time for questions.
Yeah, okay. Yes, thank you, Nuria. I love and this is great stuff. We can discuss a lot, and I just know this really new stuff. This is the best for this kind of advanced school. So one thing I wondered, so apart from feedback, you described this very well. This is really super interesting stuff. So yeah, feedback definitely must play a role. The other thing I wondered, when you trace this kinematical timescale, you trace it back, how do you really set the zero there? Is it like the densest, most compact configuration? Is it that? So
yes. So essentially, you find way of an estimate of measuring the size of your cluster, and you measure this size at different snapshots, and you see
find
that
the smallest
exactly.
size. But can it also be? Cluster formation starts before the stars start. So can that also be explain another 1 or 2 million years of offset? Because you have to condense the molecular gas. The gas starts clumping, but it does not yet form stars, and then it forms stars, but probably it contracts and then it expands again, something like that. Could that maybe, I don't know, I'm just rambling on here in a very naive way. Johnny is already protesting, so I just wondered whether that could add another million year or so of offset. No, not for the full explanation, but that, because 5 million years appears a long time for me for feedback, or not? I'm not sure. No? Okay, no, it's not. Just wondered about that thing, about setting the zero of the kinematic timescale.
But I think what you were suggesting is exactly if I understood correctly, is exactly in the opposite way we are seeing, right? Because what we see is that the dynamical ages are younger than the isochron. So the expansion begins at later stage when stars are formed.
I'm only asking stupid questions.
No.
And you're getting chocolate for it.
No. So maybe I should also say that this is really new, so I'm really happy to take any feedback or ideas.
So that would increase the offset, no?
Exactly.
Yeah. Okay.
But if the massive clouds, imagine feedback doesn't exist, it's a horrible universe, right? And then they just continue to form stars for longer. It's probably also stupid, so don't worry. And they stay bound for a longer amount of time. You can scrunch these time scales together. It'll have an apparent delta T that's small, but it's just the gravity of the cloud itself that maintains. So we know that Orion's been forming stars for way longer than the protostar lifetime, right? And everything's stuck there in this 10 to the 5 and some thing. It's not dissolving, so it could presumably in that plot, if we could push it forward, appear as a small delta T.
Yeah. So what you're suggesting is that this could also be explained with age gradient, right? So if the same cloud forms sort of different populations.
I'm just saying that maybe the stars stay, the point was that they're staying close together in the massive regions, right? I'm not sure I totally absorbed the point, right? But anyway, they're staying closer together, and you don't need feedback to get rid of the gas, to keep them together. You're saying you've got to get rid of the gas, get rid of it quickly. They're going to stay together, so you get a shorter delta difference in time between these two metrics. But it's just not clear to me at all that we need to appeal to feedback to achieve this, if we know that we have like a massive cloud that'll keep things more or less bound. Is this making any sense?
So,
or am I just confused?
No.
Very probable that I'm just
No. I think it makes sense, but but I think the point is that we are seeing currently in the present time, we are seeing that these clusters are dissolving, are expanding. So they are in the present, they are not bound for sure.
Right.
So the expansion is something that we do.
So the gas has to be gotten rid of.
Exactly.
But the time difference, it's not clear to me that it can be fully attributed to the feedback.
Okay.
Right? I mean, maybe it has to be feedback, but anyway, you got to remove the gas. But the time difference could be that things are just bound at early, I don't know.
Yeah, no, I mean, I agree with you that probably feedback is not something that, so this is the one explanation that we propose as the source that is removing the gas, because this is something that we observe in other regions. It's not necessarily to explain maybe the result that I'm finding. I think the key here is that there is this gap. So I think what we are measuring is the time during which there is no expansion. What is causing this gas to be removed and begin expanding? This, I don't know, maybe feedback, maybe there is another process that I don't know. And
I would be interested in talking anyway more about this, because it looks like in the example of Orion, feedback is very effective in keeping the gas, but it's not like getting rid of it.
Okay.
It looks like.
Okay.
Next.
Hi. So this was very interesting, thank you. I was wondering because, and maybe this is two different types of scenario, but some sort of galactic massive star forming regions you have can be on the size scales of maybe 100 or so parsec, and you have these sort of in the protoclusters them being mass segregated with the most massive members and then maybe lower mass members in the outskirts. I was wondering if there is any similarity there to the kind of clusters you're observing, or really whether anything can be said about the protocluster from these kinds of data, whether you can trace back in time to the protocluster, or whether you're more so looking at just the cluster initial conditions.
So these clusters that I'm discussing here, they are really low mass star clusters. I'm starting to look, but this is something that I haven't done yet carefully. But so I'm also interested in seeing what happens when you go when you try to continue this trend. Here the problem is that you have to go farther away, because these massive star-forming regions are a bit farther away from the sun, right? Then the problem you have is the precisions in the kinematics is not so great. But what I saw so far is that I think in some OB associations, they are already seeing that the very massive stars, they have these runaway massive stars that are beginning to expand at very early stages. So I think this would be inconsistent with this trend, right? Where very massive regions even have shorter times because already at the beginning the stars are expanding. But again, this is not something I have looked into detail, but maybe this is related to what you were bringing up. Thank you.
I might have to admit a true stupid question.
No.
No question that results in you getting chocolate too.
So what's the mechanism which is causing that free expansion again?
So I don't think we show this with the work that I did. So in the work that we did, what we see is that the clusters are expanding, so we can take them back in time and we see that in the past they were more compact.
Yeah.
Now, these clusters, if they are unbound, they naturally expand as a consequence of being in part of in the galaxy, right? The gravitational potential tends to stretch structures that are not gravitationally bound. So these clusters expand, unless they are bound, they will naturally expand. And this is also why for other clusters we see these streams and tails. You don't need any mechanism for expanding a cluster if it's a linear expansion, rather than not being gravitationally bound. So in fact, gravity would prevent the expansion, but otherwise the cluster will expand.
So that cluster's location within the galaxy itself is located at where there is a gradient in the gravitational potential or force, such that even if this thing is just sitting on its own, if it's not bound, therefore it'll be pulled apart. Is that what you're talking about?
Yes.
Okay, so it depends on the location. Then what if that cluster is sitting there somewhere that's really far away from a potential field that's across the entire cluster, that field is pretty constant, whatever, then would that expansion still occur, or?
So
if there's no external forces, why would it move?
So if there are no external forces, but only the gravitational potential, the cluster will expand, and preferentially along the direction of galactic rotation. And this happens at different galactocentric radii, and because the potential is different, this might be some details that I wouldn't be able to tell you on the spot how it works directly. But the fact that structures that were born together are expanding, this is not a surprise, I would say. This is natural as being part of in the galaxy.
No, I would say it makes sense if the field itself is. Oh, that's very slanted. But what if the field itself is flat? Then, but okay, if the cluster is close enough to the galaxy, then yeah, okay, right. Yeah, very stupid question.
No, thank you.
Yeah, I think maybe you can think about it in terms of rotation curves, right? If you're in the solar system, right, you start with all the planets in a line. Over time, they will not be in a line anymore, right? Because they have different angular velocities depending on their distance. Same thing in the galaxy. The only way that wouldn't happen is if the rotation curve were solid body, so your angular velocity were the same at every radius. But no galaxy, except maybe in the very central regions, has a solid body rotation curve. So just, you're at a slightly different distance from the galactic center, you have a different angular velocity, and so over time, even if you start with everything lined up, it'll stretch out.
I just have a comment on evolutionary tracks, pre-evolutionary tracks, pre-main sequence evolutionary tracks, and we found in 2017 a protoplanet around 500,000 years protostar, not a T-Tauri star. And clearly, I don't think the age it's precisely attributed to this star, or yes, or maybe. But we found 20 Jupiter masses planet already formed around a proto M star. So I'm really I have friends that do pre-main sequence evolutionary tracks, and they just, it's like a soup. You just put it's a recipe. They put, you know how they do it. So I'm more interested actually in the ages that the cinematics provide actually, because really there's after there's the how do you say the empty, as soon as you empty the gas, So we really don't know. We saw with filaments. We really don't know how the filaments proceed, how they evolve, everything. So imagine in a later phase of dynamics. Did you, in your paper, explained or showed or proved any kind of, or suggested any kind of process with which this would work? So this evolution, kinematic evolution. So why do you? Because I felt it was really light. That image you shown, the difference in ages. If you can show me here again. This needs the other one with the rule. No, with the other one with the rule with the disparity. Yes. Okay. I think this needs to be. If you can explain this, what you do in the paper, so to explain this difference, because here it's really beautiful. But what was your? How did you actually explain this, or suggested an explanation for this?
Okay, so I'm not
physical processes. I would say.
So I think it's really simple. So this is just a sketch or a diagram to illustrate or to explain this result here. So what we are, so essentially what we really observe in the data is that dynamical ages have this offset compared to the isochronal ages. This is like the result on the data. This is just a nice cartoon to show the other result, where we see exactly. So what I explained before.
What did you discuss in the paper afterwards? How did you actually? Did you suggest any reason why this happened? This difference? Because this is an illustration.
Yeah. So
what was the?
So what we believe is that
conclusions.
The difference between these techniques is maybe the time in which stars are still bound into the parent gas. And then, so because the dynamical traceback age in the end is telling you the moment when the stars were more compact. This may be the same or may not be the same time and when the stars were actually born and by born I mean become prime sequence stars or whatever you want to define as your time zero scale. So, in principle, if stars are formed and begin to disperse at exactly the same moment, these two techniques should trace the same time or measure the same age if you want. If they don't, it's probably that, the way we understand is that there is this time in which they are embedded into the cloud, and it's not until you remove the gas with stellar feedback or I don't know which other process.
Friction, drag.
Okay. I think we need to sort of cut this discussion off if we want to have a coffee break. So why don't you discuss over coffee?
Okay.
So I think we're going to pause here and take a coffee break. And so we come back at 35 past. Right, recover 5 minutes.
Please.
All right, 35.
And keep this stuff. We will also have final discussions and so it's not really
They switch off the lights, my body is like, entonces,
Well, I think like the isochronal ages get much better as you get older. Like, if someone tells you it's a million years old from isochronal age, but if they tell you 20 million years, that means exactly. So especially the lithium depletion ages, those are great. Well, no, but it's quite interesting. No, but I think the explanation she's giving is basically right. There's no earthly reason you should assume that the stars begin free expansion the moment they creep close to their mass. There's why would you take that?
Lithium only for beta victories and 1 hour lithium because these are slightly older. I think lithium ages cannot be 10 million years, so only for the two oldest groups we could get some Yes. So the squares are lithium.
The isochrons when the main sequence turns on basically.
No. This is pre-main sequence. At least
yeah,
you don't have, you don't see the
So how do you trust the pre-main sequence?
So at the same.
Good enough, I guess. It probably.
I think the latest versions of models, well, most of these come from the parsec models. I think they're starting to do a better job, especially, so I didn't mention, but another thing is that despite the, so for me, these dynamical things like edges are also sort of a constraint for models. So, because what wouldn't make sense to me at all is if your evolutionary model is measuring a younger age than your kinematics. This is in principle not possible.
Yes, that's possible.
This is already.
But that doesn't prove that the evolutionary times are correct.
Yes.
Right?
Yes, yes.
But obviously it's a horrible contradiction if it goes that other way, but I'm wondering if there's any stars in the lithium group that you could run the isochrones on to test for consistency. Does it even make sense?
So, sorry, can you
in the lithium group where you have like lithium's like super great. I don't work on this stuff. But anyway, it seems amazing to me because it like works and it tells you stuff. It's the revolution.
All this is lithium.
But right.
They still
But
also
can you
have a
take some of those and see if the evolutionary timescale from the isochrones is consistent with the lithium? Did you run that test?
So no difference
because there could also be an offset between them.
Yes, but this is exactly why I'm plotting so many points for the same group, because so this is the scatter that you have. So this is from isochrone, this is from lithium, isochrone. So
okay, you did a mix in a different in each whatever was available for on a star by star basis, not a region by region basis.
No, so sorry, each point. So here I'm comparing the lithium age, so the isochrone age for the members of this cluster with the kinematic age of this cluster. So it's always cluster ages. We don't measure the age of individual clusters. It's for the whole cluster you get a single age. Because you either fit an isochrone to all the members in the cluster, and these dynamical trace vectors can only be Yes, you have lithium for individual stars, but if I remember correctly, so the way to obtain the age is the last stars that have lithium. So this is a yes, no. So you in the end get the age for the whole cluster, not for each of the stars. Yes.
So they're running something on something else or whatever to makes sense. Okay.
No, I mean it makes sense, but I think it's
not if there's not any lithium.
Yeah, so but you
yeah. But yeah.
Yo tengo una pregunta. Yo no puedo, estoy buscando plástico, pero no puedo. ¿Eso sigue STARFORM? Pero no puedo mirar, no puedo a la edad de la estrella, solo lo miro por la velocidad. Entonces, tú ya sabes que lo has mostrado antes, que los pones sabes más o menos que son del mismo clase, aunque son ¿cómo le han hecho la velocidad de los en los trajes?
No es muy grande, en orden de...
O sea, como cuatro signos de tienes una... ¿Sabes lo que digo? La distribución de velocidades, ¿cómo es de ancha para que tú consideres que esos... Y si o sea, si tú tienes un clúster, has considerado clúster por movimiento, posición y edad, puedes mirar la distribución de cómo de ancha es la distribución de velocidades, porque yo no puedo mirar la edad, ¿sabes? Yo no puedo hacer una isocrona de mis estrellas porque está en el ciclo galáctico y todo vertical. Entonces yo solo lo miro por velocidad. Entonces, yo he encontrado unas cuantas que tienen cierta dispersión, pero también he encontrado otros que tienen mucha dispersión de velocidad. Entonces yo no sé dónde cortar. Entonces yo quiero ver un clúster de verdad, que sea un clúster, porque sabemos que un clúster está en una sistema, cómo de dispersas están las velocidades de ese clúster.
Sí. Claro, aquí lo que pasa es que nosotros, eso tampoco ha entrado, pero nosotros para encontrar los miembros del cúmulo hacemos un clustering en posiciones y velocidades. Por tanto, por ejemplo, runaways o estrellas que tengan una dispersión de velocidad muy rápida, igual no las vamos a
Vale,
ampliar.
entonces,
O sea que igual
¿ponéis un corte de velocidad? Es
No,
decir,
no,
cuando se separa
no.
más esta sigma de la media del clúster.
no es un corte, pero de alguna manera el algoritmo sí que penaliza estrellas que tengan una velocidad, una dispersión de velocidad muy grande. Pero, porque...
Vale, pero por ejemplo, a mí, eso es lo que me interesa a mí, vale, es un clúster, las velocidades de todos los miembros, lo que me interesa es la distribución de las velocidades. Para ver
sí,
cómo,
sí, eso sí
cómo...
lo tenemos, eso sí lo podemos hacer.
Vale, vale.
Sí,
Me han
sí.
preguntado muchas cosas ya.
Por ejemplo,
Pero sí, se me dice que...
eso es para esa muestra de escorpios y dragones que están mostrando, la que
Estos son los comunes.
sí, exacto.
Y esto es la sigma.
Sí. La dispersión de velocidad en 3D.
En kilómetros por segundo. Un poco.
Sí, sí, no. Eso. Y los que estaba mostrando yo antes son bajos.
3,6 kilómetros por segundo. Y que tengo que traducir a centro. Es poco. O sea, esto lo van subiendo y subiendo. Oye, bueno, vamos a comenzar.
Gracias. Gracias.
¿Cómo? Do you want something?
Yeah, I think I will get something.
But, Nuria, should I bring you something?
No, I'm going.
Okay.
university are you? You're at St. Andrews is UK also, right? Okay, from the accent I figured it was UK. But it's not American.
Okay.
Okay, that's true. That is still 95% of the world, but nevertheless, that's
Why did you agree to that?
That's also what I was wondering. I mean, you know, I agreed to this half a year ago, so it was, yeah, sure, I will do it. But now that was getting like sort of
This is how the organizing for the Stars and Planets meetings works, by the way. The way the next meeting organizer is selected is that the previous meeting organizers get people drunk. And then you get them to agree to stuff when they're drunk. Oh, that's how much works. It's like a slight eclectic sense of like for the Stars and Planets. The way that the theme of Kyoto is that we're all pleasant and shoot your
As you can see, Fernando has mounted this nice whiteboard, so you have it. You can use post-its, you can also write on there whatever you want to say. You can go there at night when nobody sees you. Post your question or insulting comment.
All right, welcome back to the next session. Narrating. But my introductions are legendarily effusive.
Well, I think this time we already know each other. So. Yeah, so it's me again, and as before, I'm really happy to have an interactive lecture, so please speak up at any time. I'm really happy to take questions. And clusters and associations in the numerical way, so I will continue to talk a bit more on the same, but so before I was trying to organize the talk, going from very young stuff to early, very young objects to more evolved until cluster dispersion. This time I will try to use clusters and associations to learn about the Milky Way structure, and I will take more an inside-out tour into our galaxy. Okay, so I think at this point we are already familiar with this picture. This is how Gaia sees our galaxy, and so I think we are really inside the galaxy. So we have a privileged view in terms of resolution, as I will try to argue in a moment, but also being inside the galaxy limits us in the perspective that we can have of our own galaxy. So this is how the best image or the best representation that we have of our galaxy at the time being compared to how we see other galaxies, external galaxies. So in other galaxies, we can resolve all this spiral structure with all sorts of details. We can see galaxies which have a more or less prominent bar, more or less prominent spiral arms, more grand design, more flocculent, and with all grades of detail. Also, thanks to Hubble and the new images from the GWST. So one could easily argue, so why are we even interested in our own Milky Way when we can just go there and study all these galaxies with great level of detail? Well, so the reason is that this is one of these images that I was just showing, and this is how I zoom into this image looks like. Right? So the overall picture is really striking, but when we try to zoom in, the resolution is a bit poor. And so this is this image that I was showing you, and this is how we observe as a region of a similar size in our own Milky Way. So here we can resolve all sorts of star counts of young stars. Also we can begin to see structures of the gas, several filamentary structures, all these different patterns, and we can even zoom in this picture and still see how the gas is structured with great level of detail. So this is all to say that I think it's worth giving a try in learning star formation inside our galaxy. This is the advantage, but the drawback is, as I was trying to argue in the beginning, we are inside our own galaxy. So this is like if we are trying to obtain a map of the city while we are living inside the city and never went out of it, never took a plane, right? So here we only can see how long is our street. Maybe we are in a corner and we see that our city has several streets, and we can try to build up. If we do the right experiments, the right observations, we can be smart and try to learn about how cities are organized. But it will also help a lot if we can take a plane and get our external perspective and edge-on view of the city, or in this case, the galaxy. So also by seeing images of many other galaxies, we can also learn more about our own. And in the regards of studying our own galaxy, I want to convince you, if you are not already convinced, that using star clusters are excellent traces for this galactic structure. So clusters, as we discussed in the previous lecture, are groups of stars that have the same origin. They were born together, they share the same chemical compositions, they share the same motion, they travel together through the galaxy. And also in clusters is where we have the best estimates of ages and distances. So clusters are a very good tracer of the structure and the evolution of our galaxy. As I was anticipating at the beginning, now I will try to make you a tour on our galaxy, starting from very nearby star-forming regions and associations into farther away clusters. So let's start with really our solar vicinity, our first neighbors. This is a map of 100 parsec, so this is a 200 parsec box. And our sun is sitting exactly at the center. Here we have, at the end, we would have the galactic center. This is towards the direction of galactic rotation. And so we see already that very nearby the sun, there are plenty of young stars which are grouped or clustered, as you want to call, in these young local associations, young movie groups. They are also referred. So this also comes to the problem that I think it's still an open debate on how to call all these structures. I don't like especially the term moving group, because this was initially used to define groups of stars that were moving together, but as a consequence of the galactic potential resonances of the bar and the spiral arms, but these classical moving groups were groups of stars that not necessarily have the same common origin. While all these stars that are these groups that I'm showing here, they do have the same origin. So I prefer to use either the Tail association or cluster, as you prefer. But so here the point is that already in 100 parsec bubble around the sun, we see that there are many young stars, and these are excellent laboratories for star and planet formation. So, for instance, here you have two very famous examples. Beta Pictoris is a system which has several exoplanets, and also the disk is visible. And thanks to the fact that this belongs to one of these associations, the Beta Pictoris moving group, so we know very precisely the age of the group, and this allows us to study planet formation and place this object into the right time scale of planet formation and planet evolution. And same here for TW Hydra. This is another very famous disk where this recent image from ALMA, there seems to be a region where the material has been cleared out and at a distance from the star similar to what our Earth is from the sun. So this suggests that maybe a planet at a similar distance to the sun is forming in TW Hydra compared to our system. And again, here the point is that thanks to belonging to this TWY, there are associations, we can again know precisely the age of this system. Okay, so now we try to, to open a bit the box, and this was a study done previously to Gaia. I decided to include one example to see also the gap, what we saw before and after Gaia. So this is what we used to see with Hipparcos, and already using the massive stars, the massive OB stars in Hipparcos, we could obtain a nice map of the solar neighborhood. So here we see the structure of Scorpio Centaurus, Vela. These are regions I will be discussing during the talk. And at the other side, we see Orion and Perseus region. So, and this is what we used to see before Hipparcos, and this is the map. And we can also compare it to what we saw soon after with Gaia. And essentially, so Gaia gave us much better resolution, and we began to see all the substructure of these regions as compared to previously. Especially all the low mass regions and farther away regions are much more, much better identified now with Gaia than they were before with the Hipparcos. And maybe something also to comment here, and something that you could immediately ask me, is that this region in the center seems to be empty. Well, I just mentioned that there were a lot of young stars. So why do you think this is? Yes?
Isn't the sun moving to like a bubble where there's a spring around it?
Yes, I mean, we will also refer to this, but this means that this previous, so according to what you suggest, it means that the previous groups should not be there, or because how do you relate this to the bubble?
My idea would be like the supernova, it would move the gas away from where it exploded,
So it's, yes, but I think there is something missing. So the answer is that here I said that we are mapping OB stars. So these are very massive stars, while the previous regions that I was showing you, these are really low mass star forming regions. So the majority of stars in these groups of Beta Pictoris, TWA, etc., these are mainly M-type stars. You have some KJs, but these are really low mass stars. And so this is part of the answer. The other part is that these are really low density, so these groups have at most hundreds of members, some even tens of members. So they don't even, you don't see them as big overdensities. We are just capable of seeing them because we are really, so they are really close to us. But if they were farther away, probably we would miss them. Okay, and so now we are in the Gaia era, so the rest of results that I will be showing you are works done with Gaia data. And here I'm showing a map, again, even opening a bit more the box. Now it's a 500 parsec radius, where we see that we are surrounded by a lot of clusters or substructures, and even regions that we believed to be together in the past, now we begin to resolve subgroups and again, asking for a revision of the terms that we are using. Because then here, what is a cluster? Is the whole SCOSEM a cluster, or is each of these subgroups that we analyze a cluster? So I think this is still something that we will have to see how to name in the coming years. But in the meanwhile, I think it's important to explain or mention which are the scales or definitions that we are using in the meantime, until we have a naming scheme that everyone agrees and everyone sticks to. Never gonna happen. So maybe then and we always have to explain what we mean. So yeah, this is one of the recent maps that we have of the solar neighborhood, and I will try to name some of the works that have been done in particular regions in this map. So we have already talked about Scorpius and Taurus. I will also show some more results. I will also briefly talk about Vela, and I think also Taurus and Orion. But I mean, there are many more studies, so the number of studies with Gaia is huge, so I will obviously miss many. So this is not a complete view. But so here there is a work that was done with Gaia in the region of Taurus, and we can see that again in this region already with Taurus, where this more general study used to cluster everything as Taurus, where we look into this region and try to do a more fine analysis of the kinematics of the region, we can begin to identify all of these subgroups. And also what is noticeable is that most of them correlate with the areas where we have really high extinction, so where there is a lot of gas and dust, so where the young stars once more correlate especially with gas. So this was with Taurus. A similar result has been found for the Vela region, where Tristan managed to identify all these subgroups that again correlate especially and with age. This was obtained clustering in the position and tangential velocity space. And as I was saying, also there is a gradient with age. So this also seems to be a pattern in many star-forming regions. Then also we talked a bit about Orion, so now I'm going to show the results of Josefa Grosschedel, a colleague of us in Vienna. And so she was interested in this region of Orion A and B, and she could also once more identify all the substructure, all the different groups in this region, so not only taking Orion A as one single entity, but really finding this substructure. And combining this with a set of radial velocities, one can see how these individual clusters move as a function of time. So this is becoming more and more popular with Gaia to begin to investigate the star formation histories of star forming regions around the sun. And in this case, what they found is that these clusters seem to be more compact around 6 million years ago, and since then they began to expand. So I already discussed this plot in the first lecture, so I don't need to introduce it again. This is again this region of Scorpius and Taurus, but now I will also show how this region evolves with time. So now we are taking the mean positions and mean velocities of each of these clusters, and we will evolve them with time. So this is in the present. You can probably identify the same structure as before. Here we have LCC, here we have Corona Australis, Upper Scorpius, and the big old guys at the center. And as we go back in time, we see that all these groups used to be also more compact. And now we will evolve them forward in time until the present configuration. And the sun, so this is also to show that now the sun, we are sitting in a privileged position very close to the star-forming region, which allows us to study Scosen in all kinds of detail, but this, if we were born like million years ago, we would probably not have had this chance to study these regions from so nearby. Also, another thing that I didn't mention, and that is probably important, is that when I'm showing this traceback analysis, here we are taking each cluster as a single particle. So this gives us this is easier to do in a sense than the traceback analysis I showed in the first lecture, where we used to compute the orbits of individual stars. So when we compute orbits of the individual stars, you need for each of the stars very good radial velocity precision. Otherwise, your traceback analysis is going to be highly inaccurate. Here, because each of these clusters may have many stars, even if you don't have an excellent precision for each of the individual stars, you are averaging many stars together, so you can still get reasonably accurate precisions for a cluster. So this is much easier to do than with individual stars. Okay, and now moving on, I will briefly show these results of Catherine Zucker, where she found this, or she presented the latest model for the local bubble. Essentially, this local bubble is showing or is defined by the edges, so the closest molecular clouds that we have to the sun, and this is mainly limited on one side by this Scorpio-Centaurus complex, and at the other side, this is mainly limited by the Taurus molecular clouds. And in the present, the sun seems to sit very close to the center of this bubble, and again, this could be a puzzling question, right? Because we probably, in the present time, we are convinced that the sun is in no privileged position in the galaxy nor in the universe. So the fact that the sun is sitting at the center, so, I mean, is this also puzzling anyone? Or on the contrary, so how could we explain this without saying that we are sort of unique?
There's many bubbles in the galaxy.
Okay, this is exactly one. There are many bubbles in the galaxy, and also the origin of this bubble is also not related to the sun. So it's both, and I will come to both. So first, the sun was not close to this bubble when we believed that this exploded. We were, in fact, around 300 parsecs away. And we, by chance, also sort of became close to the bubble and crossed its boundary around 6 million years ago, according to this model. And in the present, we are close to the center, but in the future, we will probably continue to escape it. However, this is really not my key expertise. In fact, Efren Marconi, he's doing a PhD in something related to this. So if you have questions on this part, I would rather ask him. So this is the first part of the answer to this question. The second part, as Rainer was saying, is that in fact galaxies have plenty of bubbles probably, and we see them everywhere. So this is not, so the fact that we are inside a bubble is probably also telling us that in our galaxy there must also be many of such bubbles. It's not reasonable to think that we are here by miraculous chance. And this region that is highlighted in this galaxy, it's because in fact this is a bubble which has a relatively similar size to our own local bubble. So again, to show that this is no privileged position or anything. Okay, and then continuing to go to even larger scales. So I'm going to show these results from Joao Alves in Vienna also, where linking the star formation regions in the solar vicinity, he found that all these star forming regions, when you get the right distances, thanks to Gaia, to all these molecular clouds, these seem to be aligned into a kiloparsec scale structure, which he named as the Radcliffe wave. And this is a coherent structure in 3 dimensions and also in the velocity space. And again, these kiloparsec scale structures are probably a common output of a common parameter of the galaxies, of our own galaxy structure, and we also seem to see this also in other external galaxies. So we could see that some of these could seem also like these long kiloparsec structures.
Wait, I protest.
Okay.
I just don't. So is it? Oh, sorry. No protest. That was just to wake you all up. I see spiral arms here. So the Radcliffe wave. So could you just help my eye here, please? That's actually what I would like to.
I think the idea is that maybe something like this could be.
Ah, okay. It's like.
So I think in Joao's interpretation, he sees the Radcliffe wave, or he sees the spiral arms rather, as being sort of segmented linear structures, right? So you kind of see it here.
Oh, yeah.
So you have like, yeah, exactly.
Yes,
so
okay, yeah.
part of the same structure, but more kind of linear. So that I think that's
Thank you. Yeah, that's what I wanted to see.
This is also related whether you think it's.
I'm asking chocolates here. They will be recycled too.
This is also a bit related, so probably we don't live in a grand design spiral arm, it's more flocculent, and part of this, so it's flocculent made out of long structures. So this I think is the interpretation here. Yep.
Do we have a general idea for this? I mean, is this kind of the structure of spiral arms, like as opposed to being kind of smooth structures but linear segmentations? I mean, does anyone?
So no.
Yeah, I mean, if you go back and read the original like Goldreich and Tremaine paper, like on spiral arms, it's I think it's Goldreich and Linden, Bell, and Pringle. It's described as a swirling hodgepodge of feathered and spiral-like structures. Is the description of what spiral arms are actually like. I don't know if it helps you. Yeah.
I have a couple more slides on spiral structure, so if you want, we can maybe discuss it. Is there another question?
So, yeah, I can tell it better. So the cause of the spiral structures. So the cause of that spiral structures might be the galactic dynamics, so the density waves. So do you think that, I mean, the linear segment is also the cause of, it's also coming from the galactic dynamics, or is there any cause of making that linear segment?
I have no idea. I'm purely, I do observation. I think I'm trying to reproduce not even what I did, what some colleagues did from the observational perspective, but I don't know how to interpret it. So maybe someone here can answer me.
Wow.
Get it back.
Okay, so if there are no more questions at the moment, maybe I go forward, and I will try to continue discussing this spiral structure now with open clusters. And before this, let me introduce the open cluster topic. And as I was already anticipating before, since the release of Gaia data, the number of articles identifying new and new clusters have exploded dramatically with time. So this is a recent list of articles providing new lists of clusters, and I'm not even sure this is a complete list. So we now begin to have many clusters that as I was saying at the beginning, can be used to trace the structure of our own galaxy. And maybe we can begin looking at the vertical structure of the galaxy. So this is in Z direction, so the vertical positions as a function of galactocentric radius. Okay? Our sun should be placed somewhere like here. And what you see here, so each of these crosses is a different open cluster color-coded by age. So the first thing that we can anticipate is that young stars seem to be closer to the galactic plane, while older clusters are more scattered. This is also probably due to the galactic evolution. Older clusters have had more time to move away from the galactic disk. Another feature that we can begin to observe is this flare, where the galactic, so the scale at a large galactocentric radius is larger than in small galactocentric regions. Another important feature is that we don't find any clusters closer to 5 kiloparsecs to the galactic center. This is probably not telling us that there are no clusters in the region, but really here we are running into a problem of extinction. The amount of extinction when we look towards the galactic center is really high, especially beyond these 5 kiloparsecs. So this is really preventing us from detecting clusters in this area. At the same time, we see that the number of clusters drop when we look at the outer edge of the galaxy. And the way the authors of this article explain and discuss this result is not that here the extinction is preventing us, because towards the outside the galaxy there is not so much extinction. What they believe is that the star formation drops, so there are less clouds that are forming outside of at long galactocentric regions. Then, using clusters to trace the location of spiral arms, so this is a bit of a historical context just to mention that already, like in the 60s or in the 30s, it was proposed that, so it was known that we live in a galaxy which has spiral arms, but trying to fit spiral arms in these plots, you will agree with me that it's rather complicated. So yeah, one could draw a line here or maybe here. So it's complicated, but the picture that we have currently, so it's definitely better. But I don't think that people working in this field agree anymore to where are the spiral arms located and what is triggering them. So last week I was in a conference in star clusters, and this slide I took it from what I learned. So on this second part of the talk, I'm just explaining what I learned last week, and essentially all these people were there, and everyone had a different explanation for the spiral arms. Already the locations, you can see that different people places the arms in different locations. I don't think they agree either on the triggering of on the dynamic region how these spirals are formed. So yeah, I think this is the main point that I got. So we know that we live in a galaxy with spiral arms. I'm not yet sure that we know exactly where are they or how they are. And to finish this talk on star clusters, so I would like to briefly mention the Gaia selection function, which is an effort that is ongoing. And the reason why this is so important is that this selection function is going to tell us what Gaia is not observing. And this is very important to not bias our conclusions based on the statistics that we get now from Gaia. So it is evident that the first works that we obtained after Gaia, these were a huge jump in precisions compared to what we had in the past. So this was great, but now we are reaching to this point where we are trying to get the last pieces of information on Gaia, and to interpret these last pieces of information, it's really important to understand which stars make it and don't make it into the final Gaia catalog. And this is going to be related on the amount of extinction, on the amount of crowding. So there are several parameters that are important in this selection function. And there are currently two different attempts into this Gaia Unlimited project. There are two different attempts into obtaining a map of this selection function. Essentially, one is forward modeling, so purely from what we know how Gaia works, from the scanning law, from the detections, the constraints that the Gaia DPAC has on the data, the cleanings before they produce the final catalog, trying to model this into a map of the Gaia selection function. So this is one ongoing project. The other one is in certain regions where we may have images which are more deeper than Gaia. We can compare Gaia star counts to what these other surveys observe, and from this extrapolate to the whole sky what should the selection function be. So this is already published, this is still ongoing, and then to translate this selection function into our census of cluster members, this is also another big step to take, and this is not immediately. So because what these people are going to provide is the selection function of the Gaia catalog, but then as usual, we usually have also some quality cuts. Maybe we are only interested in the stars which have radial velocities, etc. So we might apply another set of quality cuts on this Gaia data, and this is important. And Alfred Castro-Guinart is has published an article explaining us how to apply all these cuts on top of the selection function. But finally, another important technique, another important step is to apply, to test our algorithm and be sure which are the completeness and the contamination rates of the algorithm that we have used, because this is also something that is usually not published with all these new lists of catalogs that we have. This is great, but it's also important to produce this extra information on the quality of the list of clusters that we are producing. And with this, I don't want to bore you anymore, so I finish with my summary for this second part of the talk, and I'm happy to take any questions or hear any feedback that you may have.
Questions?
Hi, I have a question about the star cluster age and the radius from the center of the galaxy and the scale height plot. So, yeah. First of all, what are the crosses and triangles?
So, in principle, each of the crosses or triangles should be an open cluster. I'm not sure the difference. What you look at that.
And then the yellow ones are younger clusters?
No, the yellow ones are older, which are all the ones which are far away from the galactic disk. So yellow is old, blue, violet is young.
Okay, that makes more sense. Thank you.
Hello, thank you. I have another question related to this plot over here, because this is not my field, so I don't really know, so it may be something very stupid. But in the second lecture of the day, we saw this image in which we could see like the older populations of stars in the center of the galaxy, and they were all like in the thin disk of the galaxy. They were right in the plane. So I was surprised to be the older populations here going like farther away from the center of the disk.
I'm not sure which lecture you referred, but here the idea in principle is that young stars form in the disk and form also close to the spiral structure, right? And it's only later when they can migrate and also hit and move to higher.
Yeah, my question was like, why do we find that in the center of the galaxy we find all the old stellar populations if they have the time to migrate in stellar clusters?
So the question is whether the clusters close to the center of the galaxy.
Yeah, because we saw that there were like older stellar populations in the center of the galaxy, in the disk, not far away from it. So I don't get why we find that, and then here we can see that the older ones are farther away, like vertically.
I'm not sure.
But even the bulge.
Yeah.
The bulge has a different formation mechanism.
Well, but the bulge is also much thicker than this.
Okay.
And also
Okay,
you don't
then
get
I
to
think
see
it
the
might be
bulge.
me not getting the scales here in this.
Yeah, so the bulge I think you don't see it in the plot.
Okay.
Note that the X and Y axis here are not on the same scale.
Yes.
Yeah. If you did this on the same scale, it would look like a line. It's important.
Then that was thank you.
Yeah. Right. The distance between those two last tick marks is the same as the entire z-axis.
Yeah, so this is kiloparsecs.
Yeah.
This is yeah.
Other questions?
Thank you. In this last plot that you showed for Gaia's selection, it seems to me, perhaps I'm just imagining it, and perhaps you explained it and I missed it. It seems like there is some sort of symmetry that might have something to do with galactic rotation.
These lines, you mean?
Yeah, those large two bubbles, in central symmetry towards the center.
So this is the Gaia scanning law.
Okay.
This is the way Gaia observes the sky. So the way it processes and so there are regions which are way more observed than other ones.
Okay.
But this is the easy part because this is well studied. So they know which regions have been observed. But obviously, if you have been observed more often, your precisions will be better and you have higher chances to make it into the final catalog.
All right.
But when you say there's the ecliptic, like the orientation of the sun's orbit, or the orientation of the solar system in galactic coordinates. That's what the circles are.
Okay.
Hey, just going back to when you were discussing the PV substructure of different clusters.
Yes?
Just that I know you mentioned in the previous talk about the kind of like maybe algorithms or maybe machine learning techniques that maybe get used to select cluster members. And so maybe this is like a question for again like how you define the cluster. Like is there a sort of point at which you say these individual groups within these larger clusters are their own clusters or something like are there these cutoffs or categories or even like I've seen like different papers like maybe in earlier Gaia studies where they say like we take like the mean proper motion and we do a cutoff of 3 sigma 5 sigma to define the cluster. Is that sort of thing being done here or is it something more complicated than that?
I think this, so I'm not a co-author of the work, so one should look into the paper, but I don't think they did cuts. So Tristan usually uses this HTV scan algorithm. I'm not sure if he did the same here, but if it's not HTV scan, it should be something similar. So this is a clustering algorithm
It's
that...
Bayesian, yeah.
Sorry?
It's Bayesian statistics.
So basically you take the 3D positions and the 2D velocities and let the algorithm sort of look for the different overdensities. But again, these are overdensities in this space, in this 5D space that you are giving to the algorithm. No one is saying that this is going to be bound or not. This is something that you have to test in a different step.
Good questions. Everyone is exhausted and wants beer. Going once. All right. Ellen, you're going to go in once.
Can you go back to your thought just now where you were talking about you have the galactic plane and then you have the clusters on top? I'm not quite sure about the vertical scale height.
This one?
Yeah, that one. I'm not super sure about the scale, but are the clusters which are typically above the plane, or they should be typically Gobbler's clusters? The older Gobbler clusters?
No, these are not Gobbler clusters.
These are all open clusters. Right. So the Gobbler ones would be even higher.
I think so.
Way higher than that, yeah, because I wasn't sure about how many parsecs that should be.
So the globular clusters are in the halo, right?
Yeah.
So this is the galactic disk.
Okay. So somehow they would migrate upwards as they were older now.
Yes, I'm not sure about the scales, maybe.
Because apparently the older ones, the yellow ones, are typically then you said.
So the yellow ones are old, but still open clusters.
Yes, so they have more time to migrate upwards.
Yes.
Away from the plane. And why do they have that tendency?
Well, I mean, it's not that they are migrating away from the galactic plane, but it's like interacting with this, they get
so
like orbits that have higher amplitude, right? For the
Well, the globulars, they probably weren't born in the plane.
Exactly, no, I'm talking about the...
Yeah, the open clusters dynamically heat out of the plane. The globular clusters were probably never in the plane in the first place.
Okay.
Exactly, but those here, it's not that they migrate to this position, it's that the orbit is has a higher amplitude, because you also see some yellow crosses close to the center, because these are passing through the center, but probably when they continue to move up, they will move to higher amplitudes than the young ones, which will still oscillate, but only close to the galactic plane.
So they were born at a Vector's position which is very close to the galactic plane, which is why the young ones are typically there. And after they evolve, they could go in an inclined orbit. Not the orbit, as in the...
But we are still talking about open clusters, right?
Yeah, it's just being kicked up. Okay. Yeah. No,
Any last questions? Going once, going twice, closed. Thank you, Nuria, again. All right, did you want to announce?
We are closing for today, and we will meet at 8, those of you who wish to, in Das Ditas, to have a beer, maybe eat something.
Is there a location on the slide?
The location is in the Slack, and if you're not clear on it, you can ask me again, but it's